My name is Ryan Camacho. I'm a professor at Brigham Young University. And today we're going to talk about hardware, and specifically how hardware, what things we need to know about hardware to start beginning to build a quantum network and how to think about those things. I'm joined today by my co-instructor, Ian Briggs from University of Arizona. Ian, would you like to introduce yourself?
Yeah, so hello everyone. I'm Ian Briggs. I'm a fifth-year PhD student at U of A. I'm working under the Quantum Nanophotonics group, who's headed by Professor Lin Ren Fan. Yeah.
Okay, thanks, Ian. So this is the first time Ian and I have done this together, but it was really fun putting together some slides. I thought we'd start by introducing sort of an overview of what we want to talk about and also what we're not going to cover, so that you don't get too disappointed. In this course, we're going to do an introduction to quantum networks, really from a hardware perspective. There's a course this tomorrow that we're offering as part of the same winter school by Don Towsley. He will give a more theoretical or networking perspective. And then further courses beyond that go into more detail into many of the aspects that we will introduce here. So the context is, what hardware do we need to build a quantum network and why? And a basic introduction to each hardware component, what its job is, why it's important, and maybe what makes, say, a good quantum source or a good quantum detector, without a lot of detail. So those who would really like more detailed theoretical descriptions or would like to dive into these, I'd encourage you to check out the other courses that are part of the winter school. And though I found even folks who know a lot, and sometimes just a different perspective or even an introductory type material is very useful. And as Enrico Fermi says, never underestimate the joy people derive from hearing something they already know. Maybe that applies to you. Okay, so here is, again, a review of the week and what we've got. Already we've had 2 courses on the physics behind quantum networks by Mike Raymer, his gentle introduction, and then Dan Kilper just gave a course on optical networks. And today we're going to talk about hardware a little bit, introduce a lot. The course level was advertised as 1, 2, and 3, but I think we're really going to be mostly in the 1 and 2 ranges, with a little bit of 3 for certain topics, like some of the nonlinear optics or sources that some can require a little bit more. But those who are just getting into quantum networking or don't feel like they have a lot of the mathematical background, this is a perfect course for you. Okay, so we're going to do an overview. We've broken this course into 2 parts. One is our overview. We'll spend the first hour. Maybe we'll get done a little shorter, quicker than that. We'll see. Talking about entanglement and how we create and distribute entanglement using light. Those who were in the previous course by Mike Raymer will probably have already seen some of this material presented in a different way. And then really, what does the hardware need to do? Okay, so here's our picture of Alice, Bob, and Charlie. And throughout the course, these sort of squiggly lines are going to represent entanglement between different nodes. I should mention that Ian is going to monitor the chat and the questions. So that we have no questions so far. Great. So as you have them, feel free to type. If we can't get to them in real time, we'll, during our breaks, also try to answer some of your questions as well. Okay, so basic introduction. When we think about quantum networks, what we're really thinking about are quantum correlations among many parties. Quantum networks use quantum correlations. So the first question at an introductory level that we might ask is, what are quantum correlations? And to introduce that, we might play a game, a prisoner's dilemma coordination game. Suppose that Alice and Bob have been arrested and they need a shared alibi, but they don't have time to decide which one they'd like to use before they were captured. And if they don't tell the same story, they're in deep trouble, they'll be found guilty, etc. So they, as criminals, would like to have some shared alibi, but they didn't have time to decide which one they'd use. So perhaps, though, they each possess one of a pair of magic dice. Magic dice has been used in the past to sort of describe some of the magical properties or interesting properties of quantum correlation. So we'll use them here today too. All right, so what do these magic dice do? Essentially, they allow those who hold them to roll the magic dice, and if they do so simultaneously, they will always obtain the same number. So in this case, you see that Alice and Bob were able to roll their die, and they both receive a 5. Now, it is a random outcome each time, but the thing that makes these magic dice special is that whatever they roll, even though random, it will be the same for both Alice and Bob, and they can keep rolling them again and again without any other communication. So using those magic die, maybe they had a list or a code that they could send to each other that's based on random numbers only, in this case, and they could coordinate their alibi, and then they'll be okay, and they won't be jailed or whatever bad thing was going to happen to them. Or maybe some other coordination might need to take place. All right, so you could ask the question then, okay, so I get the magic dice. Where else might magic dice be useful from an applications perspective? And there are a number of places in which would show up and why you'd want something like a quantum network to perform these kind of tasks. We won't go into all of them, but here are a few possible ways you could use these magic dice should they be able to be created. Cryptography is the oldest and most famous example. So Alice and Bob would like to share secret messages, and what they lack, of course, is a secret key that can be just a sequence of random numbers. It just has to be the same sequence of random numbers shared only between Alice and Bob. And it can only be used, so it has to be generated as a one-time use. You could think of traffic management. Maybe there are many senders or receivers trying to access a singular router, and they need to sort of coordinate their timing or something about when they're going to send messages or what's going to happen. So they just need some shared information. It doesn't necessarily have to be information they send to one another. It could just be randomness. And one that we'll talk about as our sort of toy example throughout this course is a phased array telescope, in which you might want to share the same phase across telescopes in order to make a better image. Okay, I have a whole slide now for this application, which is one of the biggest ones, hopefully, that we see in the future, and that is distributed quantum computing. A quantum network can be made, or one of the principal reasons why we would like to have a quantum network is to send, transmit, and co-process information that is quantum in nature, right? You could think of, right, the early days of classical computing in which we had weak computers that couldn't process that much information, and you wanted to make clusters of those computers so that you can do more complicated tasks with them or have more memory or more processing power. It could be the case that we see many quantum computers scaling up in this fashion, and the communication links between those computers will have to be quantum themselves. Here's an example of Google's quantum computer. And then you could imagine databases or networks of such quantum computers who would like to co-process information at distance for various reasons. Okay.
Hey, sorry, I just wanted to jump in. We already have an open question. Is that couldn't the telescope just use phase recovery via math?
So it's possible. Yeah, in fact, some of the direct communication links where they do have telescope interferometry, they do recover phase mathematically, but there are limits even to that. So we'll talk about that a little bit. This is Bob Lance later on, and perhaps we can go into more detail on your question. Great question. And thanks, Ian, for catching that. Okay, so at a sort of, I guess, tongue-in-cheek or introductory level, let's suppose I wanted to make magic dice, how might I do that as our introduction to some of the quantum hardware in sort of a superficial way? Well, to begin, we ought to understand three aspects of quantum mechanics not present in classical mechanics that our hardware should need to account for. The first is quantum superposition. And by quantum superposition, we mean that some object can be in a superposition state of two quantum levels. So the example here in the picture is we have an atom. It's got an electron, and it's going to orbit this nucleus. The electrons are negatively charged, nucleus is positively charged. You see here it's just got two atomic energy levels. We can put the electron, the single electron, into a superposition of those two energy levels, and we call that superposition one in which the electron is simultaneously in two states, the excited state and the ground state. We don't have entanglement yet, though, but here's an example, right? If you just do a calculation of, for example, hydrogen, 1s and 2s energy levels, and you look at the sort of position that this electron cloud is as it's orbiting the nucleus, right? It hangs out in the ground state at about a Bohr radius away from the nucleus, but it really has a distribution, right? This electron, quantum mechanically speaking, is not in just one place. But the second excited state, the psi 200, also has a superposition. It hangs out a little bit farther away from the nucleus. And we know that the valid solutions to Schrodinger equations are ones in which we can simply add those two wave functions and create a superposition state that evolves in time and obeys all the properties mathematically that we would want Schrodinger's equations to follow. But when we measure whether or not an atom is in the excited state or the ground state, it will collapse. We'll get to that on number 3 here. Okay, so we have superposition. To make entanglement, what we need are two such atoms, both of which are in superposition, and we need to make them such that their quantum states are correlated, such that if I measure atom 1 here on the top, I will get a correlated result if I measure on the bottom. So if, say, I found this atom in the ground state, it would project, and this other atom on the bottom would also always be found in the ground state. They could also be anti-correlated. I could find one always in the ground state and one in the excited state, depending on how I set up this superposition and this entanglement. All right, but the key to entanglement is the correlations among these quantum superposition states. So our hardware is going to need to know something about how to produce superposition and how to correlate those superpositions across distance.
Yeah, I just want to jump in here again. We have another question: is how is quantum superposition different from classical superposition? Aren't they the same mathematically per se? I mean, personally, like the explanation that I would give is like when you're talking about quantum superposition, you're talking about probability amplitudes. So like we have a classical description about how probability adds, but classically probabilities never necessarily subtract from one another. But since in the quantum world, since we're dealing with probability amplitudes, where it can have a negative sign, you can actually have probabilities detract from one another. I'm not sure. Did you also want to say something?
No, Ian is absolutely right. The thing that is classically, when you have superposition, so you have like waves in water and they're superimposed, you can see the individual waves. You can see the wave functions and measure that. In quantum mechanics, the wave function itself is not the thing you measure. What you do is you take a sample and it collapses that wave function into the basis states, and you get some probability of having one of those basis states measured, and that's what you measure. You get right? So superposition is a little different quantum mechanically in that way, in that you don't have direct access to the quantum state that's involved in the superposition. Great question. Let's see, that was from Nitish. Thanks, Nitish. Okay. So we can make magic dice if we can put two atoms like that in superposition and measure, say, one of them, the other one will always collapse and get our 2 5s, for example, in this case. Okay, so here's a very basic naive way if you wanted to make a quantum network or quantum entanglement, how might you go about doing it if this is all the information you had so far? Well, here's a DIY. Maybe step one is you have to first choose a quantum object. We've been talking about atoms with a couple of levels, but there are many different types of objects that have quantum states, discrete quantum states that you could use. You've got atoms, like we talked about, photons, electrons, nuclei of atoms, Josephson junctions, quantum dots, etc. Any system in which you can sort of discretize or write down the quantum mechanical nature of that object and move it from one state to another could be a quantum object that you could use for superposition. And we're going to talk about atoms for most of this course. And so we'll stick with those for our introductory material here. Okay, the next thing you might do is take two such atoms and put them inside of a very dark box after you have excited both of them, maybe with a laser. You've taken each one of those electrons and put them in excited state, and it's hanging out there in the excited state, and you put them into a very dark box and surround it maybe with some kind of metal, so you cannot know what's going on in that box. And you know that sooner or later, you'll have a spontaneous emission event, and one of those atoms will decay. And when that happens, your box, you've engineered such that it will detect when a single photon hits it from the inside. Okay, and this is a quantum detector box that's going to detect a single photon and know that it's not two. It's going to know that it's just not one. So we'll talk about photon number resolution in a minute. But that's the idea for this particular box, is it will detect one and only one photon. And when that atom decays, you're going to know that one of those photons is now in the ground state, but you won't know which one is in the ground state. So you'll have two atoms. They're both now in superposition between the excited and the ground state, because you don't know which one has decayed, and quantum mechanically, your uncertainty produces this superposition state. Okay, your next step is you have to carefully take those atoms out of the box without measuring them, and somehow separate them, and send one, say, to a friend without disturbing the state of that atom. No measurements allowed. And now you have magic dice. To roll them, you would then make a measurement of the state of your atom. And if your magic dice are working properly, your friend should measure the exact opposite state, in this case, an anti-correlated state, to yours every time you repeat steps 1 through 5. So you have, in this case, distributed entanglement, because you have a superposition that's correlated between two parties that are not in the same place. Okay, so there are a few impractical issues with our choice of quantum object and how we distributed that entanglement. The first is that single atoms are really, really hard to control. This is evidenced by many of the attempts to develop all of the different types of quantum objects. We still haven't necessarily, as a society, agreed on a winner. We've got lots: superconducting, ion trapping, Rydberg atoms, solid state qubits. All of these are attempting to replace this idea of a single atom or a quantum object, and we need better ones, both for sources and for memories and all the things we're going to talk about today. Second, single photon detectors are really hard to make. We just drew a box around a couple of atoms, but those boxes are sophisticated pieces of hardware. And to make them work properly, we have to control all kinds of things like noise and timing and jitter, etc. And Ian later on is going to have a section of this course that talks a little bit about the current hardware or some of the history of the hardware producing single photon detectors. And the last is, well, that we're going to talk about is sending a single atom in a quantum superposition state over a very long distance without disturbing it is extremely difficult.
Just really quickly, I have another question. How do you know only one atom will decay in step 3?
You don't. So you have to do what's called post-selection on the case in which you only see one click on your detector. It's possible your detector sees 2 clicks. In that case, you have to redo your experiment, set it up again, and say, no, I only wanted 1. Okay, in that case.
It seems like we're having a bit more questions here. So one from Mark Preston has a photon and ion quanta based on independent quantum computers being linked in a quantum network interfacing the two technologies. So I guess like the question is like, have two quantum computers been linked? Like, has that historically happened? I believe the answer would be yes, but maybe you could.
It depends on what you define as a quantum computer, but just recently in the last 5 years or so, we've definitely seen entanglement distribution progressing to the place where, yeah, absolutely, we see entanglement, and some manipulation at the end nodes is beginning to happen. But whether we'd call that a full-up quantum computer being linked by quantum entanglement, I would not call it that yet.
And I think you might have already provided someone of an answer. Is like, does the box know which atom has decayed? And you would think like the answer is no, right? Where you measure one photon, but you're not entirely, the which way information is kind of obfuscated, and that's almost in a way kind of the point in some applications.
That's right. So Ian's going to talk a little bit more about indistinguishability, but in order for the entanglement to work, for the quantumness and all the properties we want about this to be right, you actually have to not know. The two atoms have to be indistinguishable. And as soon as you know that one is in one state and the other's in another state, now they're distinguishable, and you have taken those objects out of their entangled state in that case. Okay. So because sending single atoms over distance and maintaining their quantum superposition state is very difficult, a much better technology or way to do this is to use photons instead of atoms. As we'll talk about a little bit later in the course in our transmission section, transmitting photons over long distance is really the only viable technology that we know of to distribute entanglement. And that's because photons, one of the great things about photons is they don't interact with their environment very much. So the environmental noise that would destroy that quantum state in transit tends to be lower for photons than almost any other quantum object. The bad thing about photons is they don't interact with their environment. So getting them to actually at the end node or at the beginning participate in generating these superpositions is very difficult. And that interface between photons and atoms is a lot where a lot of the technology breaks down and is the difficulty in producing, in making progress in the quantum internet. Okay, so how might you switch to using photons instead of atoms? There are many ways. Here's one toy example that's slightly closer to some of the technology reality. Let's say that you have a device, a nonlinear device that can take one photon that's, say, horizontally polarized. And hey, Ian, can you guys see my mouse? Is that something that...
Yes, we can see it.
Okay, great. So here's our horizontally polarized photon, and you have built a nonlinear device that takes this photon and splits it into two photons. It does that using not a single level atom, but a two-level atom, in which you take this, you give it enough energy with this initial photon that it's going to put, you're going to put this atom into its doubly excited state, okay? And maybe you do that twice. And so now you're going to take this horizontal photon, put in this atom, and a vertical one, put it into another atom, right? Each of these atoms are identical. And so now you've got an atom that is in a spin state based on its polarization. We can talk about that later. But they're both in a superposition of being in the excited state or the ground state, because you don't know this photon. What it does is it just gets split, either goes this way or that way, but it's still a single photon. So it's in a path entangled state in which either the photon is exciting this atom or that atom. And then those atoms each will then decay, right? Or have a probability of decaying. You wait till that happens. And so if this atom on the top decays back down to its ground state, it's going to produce two photons, not one, two horizontal ones. And this on the bottom is going to produce 2 vertical photons, not 1. You recombine those in some way, and now mathematically you have a superposition state, and we can start using quantum notation a little bit here, in which you have either both atoms or both photons in the horizontally polarized state, or both photons in the vertically polarized state, but not both. It's in a quantum superposition of horizontal and vertical, and that superposition is correlated among those 2 photons that you produced.
Just jumping in really quickly here, since we're talking about, entanglement, we have another question in the chat about, in the black box and atom example, the uncertainty is related to our lack of knowledge. Isn't that like just a classical case? And, that's like it's almost in a way historically entanglement has stood in a direct contrast to sort of like what's called hidden variable theory. Is like, oh, if we don't know exactly what it is, maybe there's just this other variable that we don't know about that is actually secretly driving which way it comes from, or which polarization it is, or what have you. And so there's kind of like a lot of games you can play with correlations to prove that no, there is no secret hidden variable that we're just unaware of that caused these types of states to emerge. Did you also want to?
No, that's great. Yeah, this was actually one of the things a lot of people thought about when quantum mechanics was developing. How do we know it's not just classical correlations? So Mike Raymer's course did a great job, I believe. I didn't attend it this time, but I've seen him before, talking about some of the ways we know that these correlations are not classical. Yeah. Let's see. Do these photons have color? Yes, they do. The color is given by the energy difference between each one of these quantum states in the atom. Energy is equal to h bar times omega, where omega is a frequency. So if you have some energy difference between the atoms, it directly translates into a color of a photon that's going to be produced. Okay. So now if you wanted to distribute this particular type of entanglement between your photons, one thing you might do, and there's many other ways to do this, is take these 2 photons and look at cases in which you can send one photon, say, this way, and another photon down to this other person, and they're waiting with their own atoms, right, that they have locally. They haven't had to carry them with them somewhere. They have their own atoms. And this atom, say, and on the top only goes to the excited state if a horizontally polarized photon comes in, right? Both of them are. And so now you have these 2 photons going, and they're only absorbed if they're horizontal. Now they can measure their atoms, and those become their magic dice, because they transferred the entanglement that was in the photons back to a matter-based entanglement at the other side. Okay, so that's the basic idea of our launching point, and we wanted to explore a little further in this class some of that hardware that's required to do jobs like the one that I've just described. And we want to use many, many entangled photons to create a network of these correlations and start to perform tasks now that we have entanglement as a resource across our network. Okay. So what hardware do you need to build a quantum network? Well, you need a lot of hardware. The stuff we're going to cover in this course is the generation of entanglement, or the generation of quantum states in photons. Frequency conversion, because oftentimes you want to convert the color of the photons to something to be transmitted with less loss. Transmission, how does it get from point A to point B? Storage and memory, how can we hold on to this quantum state for some time long enough to perform an operation, or to wait until entanglement in other places builds up? And finally, detection. What we are not going to cover in this course is all of the control hardware that needs to manipulate the atoms and produce the different states using lasers and RF pulses, etc. And we are also not going to cover classical communication, this overhead or this extra communication that needs to happen in addition to sending the quantum objects. You need a lot of classical communication that happens. In fact, probably most of a quantum network is going to be, the hardware is going to be classical communication. Hopefully, and Dan covered a lot of that, and that will be covered more in later courses as well. All right, I see a whole bunch of questions coming up, Ian. You just let me know if there are ones we should answer now, okay? Okay, what type of quantum networks are there? The answer is there are many, many types of quantum networks. And to make a course like this, we have to kind of choose some concrete examples of specific networks while giving you a flavor for the many types of other topologies and networks we might discuss. One principal demarcation or way to separate different types of quantum networks or entanglement is discrete variable versus continuous variable. So when we say discrete variable, that's kind of like the same kind of way you would think of digital versus analog electronics. In digital, right, we have only zeros and ones that we're dealing with. In analog, we can have some continuous state that we measure. Quantum mechanics is the same. If we are dealing with the eigenstates or discrete levels of atoms, for example, we could label each one of those a 0 or a 1. We call that discrete variable. If we're dealing with, like, say, numbers of photons, 1 photon, 2 photon, 3 photon. These integers, we'd say those are discrete states that we can use for quantum mechanical information processing. Continuous variables are a little bit different. Let's say we are talking about the numbers of photons. You can create quantum states that have many, many photons in them, right? There's not just 1 photon or 2 photons or 0, but some distribution of photons. And oftentimes in the continuous variable case, which we won't cover a lot in this course, you would like to restrict yourself to Gaussian operations because they're much easier to describe both theoretically and easier to build experimentally versus non-Gaussian modes. And when we say Gaussian, we mean any state that can be described with a mean and a covariance matrix. And Gaussian functions that you apply to those, things like homodyne or interference that we won't go into a lot of detail in this course about, are ones which can transfer a continuous variable quantum state that's a Gaussian state into another Gaussian state. Okay, so I'm going to briefly for a little bit here just introduce the rest of the course in this introduction and talk about things that you should be sort of preparing to learn or ask questions about. The first topic we're going to talk about is hardware is quantum sources, right? So the key concepts you might want to ask, okay, what atomic systems can be used as sources? How do you control the nonlinearities, right? Like this 2 photon concept that I talked about to achieve something called phase matching so that both these photons are traveling at the same speed. How would you then characterize such a source? Using concepts we're going to introduce called fidelity, indistinguishability, efficiency, and how can you enhance the interaction between the photons and the atoms? I'd said already that one of the best things about photons is they don't interact with their environments, but when they get to the atom, we need them to strongly interact. So how do we do that? Cavities are often the key to doing that. And then once we have these sources, how can we use them to create entanglement, say from single photons or biphotons? And as a bonus, we'll touch just briefly on how to create continuous variable entanglement using squeezed light, a special type of Gaussian continuous variable state. Okay, and broadly, we'll talk about single photon sources and biphoton sources. We're going to talk about frequency conversion. This idea that the color of the light coming out of your atom that you want to distribute may not be the best one for transmitting across a very large distance. So we're going to talk about how, why that is, and then how we can transmit quantum information by first converting it to a different frequency and what hardware might be required to do that, and the different things people are looking at to solve this problem. When we talk about transmission, the key concept is that in a quantum network, no amplifiers are allowed. So we're going to have to find a way to transmit our photons while taking into account the fact that we cannot amplify them, because what's not allowed in quantum information processing is cloning, right? Amplification is like taking one photon and saying, I want many, many of these, so I'm going to amplify it so that I can have more of them. So in case I lose one, I still have one left over. But the no cloning theorem says, We can't actually perfectly copy any quantum state, much less an entangled state, that we already know what that state is. So maybe there's ways around that. And what considerations should we have when we're building this? Maybe we'll talk about repeaters and memories and how many hops are we can make without disrupting our quantum network too much. We'll talk about quantum memories. This is the idea that these will show up as yellow circles in this course. And so if you have two nodes that are entangled by the squiggly line, and you have the ability to keep that quantum state for some length of time, we'll call that a quantum memory. We'll talk about what kind of quantum memories are being explored. We'll introduce, or at least review, this idea how teleportation is the basis of extending entanglement. And again, touch on the importance of this cavity enhancement, because this is all about that photon matter interaction at that point. We'll talk about quantum detection. Ian's going to introduce the different types of quantum detectors, avalanche, superconducting, etc. Why it might be valuable to have photon number resolving detectors, and why that's a challenge to make. And how might we compare the performance of different quantum detectors, given that you want to make some kind of network. Okay, finally, before we end the introduction, I want to introduce the application example that we'll come back to a few times in this course, to give maybe some concrete ways to talk about the hardware that we're going to introduce. And the example Ian and I have chosen to sort of guide this part of the discussion is our quantum telescope. So here's a basic introduction to the way a telescope array, ones that currently operate, might be used in some way. Why do we have telescope arrays and not single telescopes? How are they able to better resolve the angular position, say, of stars or other stellar objects? So let's say you have some region of the sky, and in it you suspect there are two objects. Maybe it's a binary star or something like that. And you want to measure something about these with enhanced angular resolution. You want to make a picture in which you can distinguish one of these from the other. So what you do is you create two telescopes, and they can each receive light from this point in the sky. And you choose a star, say, that's weak enough, or you filter it out that's weak enough, such that only one photon at a time is reaching your telescopes. So the state of that photon, as it's traveling down, it's going to either go to this telescope on the right, or that single photon is going to go to this telescope on the left. And you assume that the light is weak enough that even if there's a probability that you get multiple photons coming at a time, it's really small. And we'll talk about the difference between weak coherent states or weak thermal states later versus just pure single photon states. But let's say that you've got one photon and it's coming from this distant object. Okay, so that photon is in a superposition state of having gone either to the right telescope or the left telescope. So you can write down the quantum state as either there being no photons at the left telescope and one photon on the right telescope, or one photon at the left telescope and zero photons at the right telescope. But there's one extra term we need to add here, because the distances to the two different telescopes are not necessarily the same. In fact, if you use just some simple trigonometry, the way we've drawn it here, this telescope on the left is going to accumulate a slightly extra phase, phi, given by the separation between the two telescopes and the wavelength of light that it's emitting. That extra phase is going to show up in our quantum state. And if we can determine that phase, if we can somehow figure out what that phase is, the phase difference between the photons coming in these two different paths, we can resolve angularly, right? We can figure out exactly what position in the sky that photon was coming from. So the classical solution is called direct detection, and we just simply use interference. between those two paths to find phi. So we take the photon that's coming here and the photon that's coming to this telescope on the right, and we put them on a beam splitter, and the phase relationship or the phase difference between those two photon paths coming will result in destructive and constructive interference as we vary the make slight variations, say in some phase delay or some delay to that beam splitter, and we can map out exactly what phi must have been by looking at the fringes. And that is one way you can use direct detection to do that. You can also, this is similar to the concept proposed by one of our questioners earlier. It says, well, you can figure out the phase difference in a similar way, right, using mathematical and numerical reconstruction, right? But you're always limited, right, by phase noise that might be introduced either in your system or after your system. In this particular direct detection case, right, if you have any loss in any one of these paths between the beam splitter, between the two telescopes and the beam splitter, then your quantum state is automatically disrupted and it's no longer usable because you no longer have a photon for those cases in which you have loss. So that's a problem. In addition, the longer you make the separation between your two telescopes, the bigger B gets, the harder it is to stabilize this interferometer, this phase-sensitive measurement you're going to make. So currently, telescopes are limited only to like a kilometer, maybe a few kilometers, these earthbound phased array telescopes, precisely for this reason. It's really hard to control the phase and the loss, even and make sure that you can be very, very long to angularly resolve these. Okay, so one of the proposed solutions.
Really quick, sorry to interject here, but really quickly, we have a question about some like clarification of language, just for those who are like really new to these types of things. They don't like see these sort of types of wave functions like with kets, and they're not entirely sure like what that even means. So I think it would be, just a little bit important to clarify that, where like we usually express these sort of quantum wave functions as these ket vectors, and usually when you see like two ket vectors sort of like conjoined together with each other, almost like they're multiplied together, or sometimes you might see some like joined together ket vector where it's 0, 1 or 1, 0. So that's kind of like refers to two individual subsystems that are simultaneously in the same state. So it's like you have a ket vector here, the first ket vector, which refers to L, which is like the left telescope, and a second one, R, which refers to the right telescope. So when you see 0, 1, that refers to 0 photon in the left telescope and 1 photon in the right telescope. I hope that maybe just clears things up, maybe just a little bit for people who maybe are not really familiar with this notation.
Great, yeah. And those who are more mathematically inclined, what this mathematically means when I put these two next to each other is actually a product state. So you could think of this as some matrix, and this is another matrix, and you perform the outer product and create some larger matrix with extra dimensions. But yeah, you can think of it just like Ian talked about, is these are just representing the state of the photon in the left and the right, and you add them together in superposition. Okay, so the solution proposed by Gottesman back in 2012 was, hey, well, we know that entanglement is like, well, he didn't say it this way, is like these magic die. If what you need, right, is to sort of measure something about the correlations, the phase correlations between two things, why not just use entanglement to perform that operation? So he proposed that, well, what if we had two telescopes that actually had some shared entanglement, had atoms that already, when you measured one versus the other, would produce some correlated result, right? So instead of locking the path lengths of an interferometer, right, to always have the exact same path length so you can control maybe you just lock two atoms using entanglement so that no matter how you measure them, they're always going to give you the same result. And so the problem here is you need to produce that entanglement and keep track of it. It's a very challenging technical problem. But inside, you might imagine that now the telescope looks like this, right? You've generated some memory that holds on to the atoms that are in superposition states that are entangled, but now you have two of them, right? And they're just waiting around for when some photon comes and strikes, say, another atom that you've got ready to absorb that photon. And then you have both those atoms emit their quantum state into a photon or couple them in some other way onto a local beam splitter. And using that, you can in fact measure the phase difference non-locally over a very large distance. In fact, the distance doesn't matter at all in that case, so long as you can have high quality entanglement. So, conceivably, you could do this across continents, across galaxies, and you can make your angular resolution as fine as possible. There's no limits quantum mechanically to doing that. Just technologically, as perhaps we'll talk about a little bit more later, is a very, very technologically challenging problem to create and preserve that entanglement across those two distant telescopes. Okay, so that is the end of our introductory section. What we're going to do is take about a 5-minute break before we start our dive into particular hardware components. During that time, you can ask questions. I'll be around, Ian might be too, or go use the restroom. I was going to actually, during the break, also throw up some chat GPT and ask it some questions about quantum to show folks I've been having fun doing that, and I wanted to share that with people too. Ian, did you have anything else before we end this introduction?
Yeah, I'm sorry if I didn't get to everyone's questions. It's great. It's great that you guys have a lot of questions. It's like we're trying to maintain the general pacing of the course, but we can take this time to address some questions that I might have missed. So Edward Beadle asks, does direct detection as described require a photon hitting each telescope at the same time? How do you enforce this?
So no, well, you assume that in this geometry, the one we've built here, that these telescopes are really, really so much closer than the distance all the way out to those stars, that effectively, because you know the distance between your telescopes, you know that photon, right, will arrive almost simultaneously to those two detectors, or at least you know exactly what the path length difference is between, you know what B is. So if you know the distance to the stars or something close to, or the angle, all you don't know is phi. I don't know if that helps.
We also had another question by Edward Beadle. I think this was one of the earlier diagrams, is how does one photon create two photons? At a top level, it seems we are getting more out than we put in. The energy gained by the atom seems less than the energy out.
Okay, great. Yeah. Actually, Ian, you want to address that one?
Yeah, I'm not entirely sure which diagram it's referring to.
I put the one back up where I have one photon going in and then two photons coming out. Maybe this was the one that prompted the question.
So
we've got some nonlinear process happening there. Yeah.
Yes. There are nonlinear optical processes in certain materials that if you put one photon in, you can get two photons out. And you might say, it's like, oh, how is energy conserved in that case? Well, as long as the sum of frequencies that you put in is identical to the sum of frequency that you get out, then energy is still conserved in that case. I hope that clarifies some things.
So Mark Ruffini asks, do you need single photons, or you can calculate the fringes from classical interference? Yeah, you can. In fact, this is the way it's almost always done, is you just calculate it using classical interference. I just introduced it the way that Gottesman and their paper wrote it just so we can introduce what the quantum state might look like if it were single photons. But really, you can do it with many photons, and that's okay. All right. Let me share something else. I think this is what I want to share. So I've been having a lot of fun playing with ChatGPT. So during our break, maybe I'll show you. So for example, I might between quantum superposition, quantum entanglement. An error occurred. Oh, probably I need to refresh. Okay. Position, quantum entanglement. So the chat bot's going to tell us. See if we got it right. So I'm just blown away that the AI knows this kind of stuff.
Yeah. At first I was like, oh, it's just printing the definitions that it found on Google. But then it's like, oh, the difference between these two systems is actually this. It's like, oh, wait, it actually has some sort of, maybe it did just randomly pull that, but at least knows where to pull, you know. Like we needed like a difference between superposition and entanglement, and it specifically searched for that. Yeah.
That's right. Yeah, I thought that was pretty cool. And let's see, what's another one? What types of, let's see, let's just ask it for an opinion. What is the best quantum memory? The best type of quantum memory? See if it wow. So it knows even some of the benefits of different types of quantum memories. Oh, and it's not gonna make it. Okay. Yeah.
I mean, I guess that's like technically the right answer, you know, there is no traditionally best.
So if anyone has any suggestions for our chat GPT AI, you can put it in during the break, or we can ask other questions. We'll get started in 5 minutes with other. So Ian, I'm gonna stop sharing, and you have the next section, right?
Yeah, I have the next section up and ready.
Okay, so I'll apologize. I was losing my voice a little bit. I had something earlier this week. When will we have a quantum telescope? Okay, so that's pretty cool.
ahead and share my screen. You guys can see that just fine, right? Can you guys see the presentation?
Yeah, I see it.
Okay, cool.
Oh, thanks, Mike. We've got an extra expert online here who can help us answer questions.
We also have a question by Ellie Cox, who says she would like to understand better why it is desirable to use polarization orientation to store a state of a qubit in a photon. And like, I'll talk a little bit about this in sort of my part, where it's like there are multiple ways that you can encode photons to store information. One being like frequency, time, polarization, path. And there are advantages and disadvantages to all of those choices. But yes, polarization is one of the more popular ones, I suppose.
Yeah, polarization is advantageous, especially when you're propagating through the atmosphere or places in which you might have some free space link, and you're worried about, say, turbulence or noise being accumulated, and sort of the direction that the field is oscillating tends out to be pretty insensitive to those kind of fluctuations. Whereas if you encoded it like in the phase of the photon, and you hit some turbulence, now your quantum state has lots of noise on it. So let's see, how do I address these questions that say answered? Oh, you just.
Oh yeah, I just typed in some answers to some questions. I didn't want to interrupt every single time. So I tried to answer some of them the best that I could.
Perfect. Okay, so we're at 2 o'clock. Ian, why don't you lead us into our next section?
Yeah, sure. So the first part, we kind of gave like a really general overview of like the different aspects that we need from our hardware. Now I'm just going to go into a little bit detail into each individual pieces one by one. Next slide, there we go. So the first piece of our quantum network is sort of a photonic quantum source. So in order to transmit quantum information in a quantum network, you generally need a state of light in which the quantum behavior is readily apparent. And that usually means that we need sources that emit on the single photon level, where you have singles amount of photons in a singular mode. A first educated guess that you might give for a single photon source is you just take laser light and you just attenuate it way down to the point where the average number of photons is on the single photon level. And this is like a really simple idea, but unfortunately, your first guess isn't always the best. Because if you end up doing that with coherent states, you don't really see the characteristic photon statistic that you would want to use for quantum experiments. So I'll talk about two general ways that you could generate single photons. One being using fluorescence from atomic systems, and the other called spontaneous nonlinear processes. So the first one I'm going to go over briefly is fluorescence from atomic systems. And this could be a variety of things, a variety of different systems, such as trapped atoms, ions, and molecules, where you have like singular atomic units sort of trapped in a confined space that you could excite single photons out of. But you also have more solid state systems like quantum dots, or what are called color defect centers. One such example is shown here. If you can see my mouse, if you have like a lattice of carbon atoms in diamond, and then you have a point defect of nitrogen and a vacancy center that accompanies that, and you can use that as like an atomic-like structure with its own discrete energy levels, which is actually depicted over here. So the general way that you operate these as single photon emitters is you have some sort of external control. Typically, this is in the form of like a pulsed laser to put the system into an excited state, and a single photon is emitted upon relaxation to a lower level state. The nice thing about these atomic systems is that they're relatively deterministic on-demand photon sources. So you can very precisely control when that photon is going to be emitted. But the downside of using these types of sources is that the setups for these types of sources tend to be really bulky. Here's one example shown here on the lower left called a magneto-optical trap, which is what you use for trapping atoms, ions, and molecules. And often you have to cool to like single Kelvin or even millikelvin levels. And another problem that you tend to run into is that if you have multiple of these emitters, the indistinguishability, which we'll talk about later, tends to be compromised by any effects in the environment, like some sort of charging effect, or you have some surface defects. So the second source of single photon emitters is by using what are called nonlinear sources. And this is, of course, where I have to say I'm very biased, because like a lot of the research that I do in the lab involves nonlinear sources. But historically, these types of sources are much more common than atomic system single photon emitters, simply because they're relatively simpler to fabricate, and you don't need as sophisticated an apparatus to operate these types of single photon sources. For example, you don't need to necessarily like cool to like single Kelvin levels to operate these types of sources. So these nonlinear sources are what are called spontaneous photon pair sources, which spontaneous meaning you cannot precisely control when the photons are going to be emitted. But the saving grace of these types of sources is that when they are emitted in pairs of photons instead of just one photon. So in a lot of applications involving single photon sources, you'll use one of those photons in the photon pair to indicate the presence of or herald the other photon. So the way that nonlinear sources work, or indeed nonlinear optics in general, is from a Taylor expansion of electric susceptibility, where you have the polarization of your material being dependent on the incoming electric field. Usually when you're just talking strictly about linear optics, you would only pay attention to this chi1 term, which would give you the refractive index. But when you include these higher order terms, much more interesting things can happen. In general, with nonlinear optics, what I was talking about before is that you could use these nonlinear phenomenon to convert photons from one frequency to another, just as long as energy and momentum is conserved in that process. And in general, there's two different classifications for nonlinear optical processes. One being sort of second order nonlinearity, which is dictated by this chi2 term. And specifically for single photon emitters, we use something called spontaneous parametric down conversion, which is given by this figure here, where you have a photon at frequency 2 omega, and through this interaction that is facilitated by this chi2, you get 2 photons at frequency omega. And then you also have spontaneous 4-wave mixing for a third order nonlinear process, where the only difference here is that instead of inputting one photon at frequency 2 omega, you have 2 photons at frequency omega. And this is kind of shown by this energy level diagram here, where you're putting pumped photons, and the photon pairs we generally refer to as signal and idler photons. So I'm going to be covering a little bit more on second order nonlinearity. One reason for that is that although second order nonlinearity isn't necessarily common in a lot of transparent materials, but in the materials that have second order nonlinearity, the strength of that interaction is much, much larger than any third order nonlinear process that you can achieve. In general, second order nonlinear process tends to emerge from an anisotropic geometry in a crystal, or we say a crystal lacks inversion symmetry in at least one direction. Over here, I've given an example of one such material called lithium niobate, which is used a lot in second order nonlinear optics. And I just want to hammer home again that in order to have an efficient generation for these single photon sources, you need energy conservation and momentum conservation. But you'll notice here, energy conservation just means that energy you put in is equal to the energy put out. But these omega 1 and omega 2, they don't necessarily have to be the same. There are some cases where you do want them to be the same, but which is referred, and when it is the same, that's generally referred to as a degenerate nonlinear process. But when they aren't the same, that's referred to as like non-degenerate nonlinear process. I should also mention that the types of nonlinearity here is directly dependent on the crystal properties here, which is described by this matrix equations, where you have combinations of input electric field on one side and the nonlinear polarization on the other side. So the general shape of this matrix, which dictates the relation between nonlinear polarization and electric field, that's largely decided by the material geometry. So for whatever nonlinear process that you're going to use, you generally need something called phase matching. And the way that you can think about it is that in general, like if you have multiple optical modes within your material that are they're interacting with each other, if they're both going at different speeds, they don't have time to interact with each other. So you're not going to get an efficient like interaction going on. So in order to have efficient nonlinear generation, the photons at different frequencies should be traveling at the same phase velocity, which is generally given by this delta K here, which you can put in terms of the difference in refractive index. And there's two general ways that you can do this. One being dispersion and engineering, where you phase match the fundamental mode spatial mode with a higher order spatial mode for the second harmonic frequency. And that's what's shown in this little plot over here, where you can see how the effective index for the fundamental and second harmonic modes change with the waveguide width. And you can see for one particular waveguide width, the fundamental and second harmonic modes both have the same effective index. Another way that you could phase match a nonlinear process is by using something called quasi-phase matching, where you periodically switch the direction of the crystal to compensate for the dispersion of the photons. As long as, and this is sort of like for first order quasi-phase matching, you would use this sort of period. And the way that you can kind of think about it is that through these diagrams here, where these arrows in complex space refer to the generated electric field of the nonlinear process. So without phase matching, the electric field accumulates a phase, and you ultimately end up with destructive interference. And so all you do is end up going in a circle in this complex space. With phase matching, because all the phases are aligned, you have it all adding with each other just in one direction. But with quasi-phase matching, you start going around the circle, and then halfway through the circle, you switch the direction of the nonlinear crystal, which effectively flips the phase of the generated electric field. So you can still get an accumulated electric field overall. All right, so now that we've discussed ways to generate like single photon sources, what exactly makes a good photon sources? And there's three general metrics that we want to pay attention to. One being fidelity, which is how closely does the produced quantum state resemble the ideal quantum state that you want. Another being indistinguishability, which is, are the photons that are produced by multiple sources, are they identical in all degrees of freedom, which is extremely important if you want to interfere photons with one another. And the last one being efficiency, which is what brightness can be achieved per pump power. It would be nice if you could have like a photon source that is like ideal in every way, but if you had to wait like hours or even days to get the relevant photon statistics, or if there's a source of noise that overpowers it, then that's not going to be just a useful source in general. So that's where efficiency comes in. So one vital tool that we use for characterizing single photon sources is what's called coincidence detections.
Hey, Ian.
Yeah.
I just want to pause. There's some questions that might be relevant to discuss in real time here.
Right.
So John Kim wants to know how we might define a quote ideal quantum state, and David Liu is asking for an example of a nonlinear source. I think those might be two ones to discuss if you have ideas already.
Yeah, I mean, so there are like several different ways to implement this, one of which we'll talk a little bit more about later. But in terms of like, this is an example pulled from a paper here of what's called periodically pulled lithium niobate, where you have like a single crystal of lithium niobate, and you switch the direction of the crystal axis of the lithium niobate using a really intense electric field. And you can also use sort of like a nanophotonic platform where you have waveguides that are microns across. So you can see the cross section of that photonic structure here, where you have this aluminum nitride trapezoidal waveguide that is embedded in silicon dioxide on top of a silicon wafer. So those are two examples right there of like one where you can use these bulk optical elements as well as nanophotonic elements. I should also mention that you could also do this in a fiber. If you like, if you dope a fiber in a particular way, you can get access to other non-linearities within that fiber. Yeah, I hope that answers that question.
Great. And in terms of the ideal quantum state, do you have any thoughts on that? When you put ideal, what does that mean?
Yeah, I mean, so ideal being well, so here are like three metrics that you would use to say like what exactly is ideal. And usually it means that like any sort of
I have a thought if you want me to start.
yeah, that'd be much appreciated, actually. Yeah.
Yeah, no problem. So when you're doing quantum information processing, there's, like we said, a number of quantum states that you might want to use. And typically you choose one and say, okay, I would like this particular state. The very common ones are called Bell states, for example. The one I wrote for the quantum telescope, no, for the two horizontals and two verticals. That's called one of the Bell states. There are 4 Bell states. So you might check, okay, do I really have a Bell state, or is there a little bit of extra noise? Is my superposition really 50-50? Is that ideal or not? There are new quantum states being investigated that are more robust to noise and have other properties that help them. But in general, the theoreticians often come, oh, if we had only this quantum state, right? They write it down mathematically and they plug it into the quantum optics equation, say, oh, this would be ideal. And then they turn it over to us experimentalists, say, can you make this quantum state? So we try to make some new source, and it's not, we have to measure how good did we do. And so it's not ideal if the theorists don't like it, I guess is the.
Yeah, the way that I usually explain it is like the quantum information theorists will have these black boxes, and they'll say, okay, what can we do with these black boxes? And then it's, the experimentalists or our job to say like, okay, how do we actually build the black box? Yeah. All right. So let's keep going here. So like I was saying before, like a vital tool that you would use for characterizing a single photon sources are coincidence detections, or also known as like what's called like a G2 measurement. And in terms of like creation and annihilation operators, it's given by this expression. If you have no idea what this is, just don't stress out about it too much. But like in the lab, the way these coincidence detections look like is you generally have 2 streams of photons going to 2 detectors, A and B, and then which goes into timing electronics, which is plugged into a computer. So the way the data looks like is you have channel A and channel B, and you have a set of clicks, which are basically timestamps of when those photons arrive at these single photon detectors. And you say that if 2 photons arrive at the 2 photodetectors within some time window, you consider that as a coincidence event. And the like major metric that you're looking for is how many coincidence events you get per second. But you can't just measure it for one time, because there might be sources of time delay within your system, and also the coherence of the photons that you're using will also affect what you see. So we usually, what we do is we delay one channel with respect to another here, where you're kind of sifting one channel through another, kind of like a convolution type operation. And for that particular time delay, we then measure the number of coincidences again. So here's, and based on those coincidence as a function of time delay, you construct your histogram, which is what you use to characterize your source. And here's just one example, as shown here on the right, for a nonlinear source where you have photons created at 1556 nanometers and 1544 nanometers, and you see that for one particular time delay, you get a lot of coincidence events, which taper out to around 0 at very large time delays. And when talking about coincidence statistics, there are 2 phenomena that we want to pay attention to. One being photon bunching, where your the number of coincidence events is like very large. You get a very strong peak at some time delay, or photon anti-bunching, where you get like a dip in the coincidence detections for some time delay.
Hey, Ian,
Yes.
there was a question about just the x-axis of what that meant on that coincidence plot.
Oh yeah. So this x-axis here on the lower right hand, it refers to the time delay. So the relative time shift from relative from one channel to the other. Right here, I refer to that sort of like sifting operation where you kind of using post-processing, you sift one channel through the other. So that time delay tau is the x-axis here. I hope that makes a bit more sense. Oops. Oh boy. Oh, I'm sorry.
We're still back on there. A couple questions if you think we have time. Otherwise, we can answer them. I can answer in the chat, and you can move on.
Yeah, it might be better to move on. I'm just having some trouble here. I can't move the okay, here we go. I got it. All right. So next, so the first metric that I talked about was fidelity. And usually in terms of single photon sources, people call that purity. So purity is essentially a measure of how close can you get to a single photon in a single optical mode. The way that you generally measure purity is through again like a coincidence measurement called like the self-correlation function, and we use this called a Hanbury-Brown twist interferometer to measure purity. So you can see this ordinary light source, which you can consider like an incandescent light bulb. If you send this into this interferometer where it's split by a beam splitter and you have your two detectors on each arm, you tend to get photon bunching at some time delay. If you use, say, like laser, which outputs what we call a coherent state, the correlation measurement here will just be flat with respect to time delay. But if you have like a non-classical, like a single photon source, and you send it into the system, you should actually have some time delay at which the coincidence go to zero. And the way that you can think about it is that, you know, if a single photon is entering this beam splitter, it'll either go to detector 1 or detector 2. You know, it can't go to both. So at some time delay, you can't have two photons arriving at the detectors at the same time. So there's generally two different ways that purity that purity is non-ideal. One being photon number, which is due to higher order emissions. So in the case of this, where you want psi equal to 1 photon, instead of that, it's actually in a quantum superposition of 1 photons and 2 photons and 3 photons. So those higher order terms will sort of corrode what photon purity you will see. The second has to do with the spectral content of the photon, which is a bit more complicated. It has to do with something called Schmidt mode decomposition, which is generally what you talk about when you're talking about photon pairs. And the way that you can generally think about it is that you have this joint spectral density between the photon pairs, where you have like the frequency of the either photon and the frequency of the signal photon. And the measure of spectral purity is generally considered of like how separable these photons are, or this joint spectral density in terms of these orthogonal functions in frequency. So in this case, this is a case that is like highly separable, where you would only need one term in this expression to fully characterize it. But this is sort of but on the other hand, this is sort of on the bottom, this is a highly correlated in frequency photon source. It's actually a source of frequency entanglement here, where we actually need multiple terms in the summation to fully describe it. So the second metric was, again, indistinguishability, which is how similar are the photons that you are producing. And you want them to be as similar, usually you want them to be as similar as possible in all degrees of freedom, which include spectrum, time, polarization, and space. And so indistinguishability, when you're talking about identical bosons, it provides an upper limit of how well you can interfere the photons. Generally speaking, and you can intuitively expect that you can get more indistinguishable photons if it's coming from the same physical source, which you can use time multiplexing techniques to make that happen, or you can use other clever techniques. But if you have, say, multiple single photon emitters, you generally need some tuning mechanism to ensure that the photons that are produced by both sources are identical in every way. And the way that we measure indistinguishability is what's called like an HOM interference experiment, where you have two photons that you want to measure the indistinguishability from, and you have a delay line on one line. It's very similar to like the purity measurement for purity, but instead of just one source, you have two. And again, the amount of indistinguishability is how close does the coincidence rate get to zero for some time delay. So the last metric I'm going to talk about is brightness. And the kind of frustrating thing is that the exact definition of brightness is actually going to depend on what platform you use. For example, for quantum dots or single or trapped atoms or ions or what have you, the brightness is defined as the probability of an emission event per excitation event. But for nonlinear sources, it's defined as the number of photons, number of single photons you get per unit pump power. And that's in case of parametric down conversion. If you're using four-wave mixing, it would be per unit pump power squared. And sometimes you will also see it normalized in terms of bandwidth. And in terms of the overall efficiency calculation, there are several different smaller efficiencies that you have to consider. One being, conversion efficiency for nonlinear sources. How well can you couple into and out of the system? As I said, excitation efficiency, as well as your detector efficiency will also go into the brightness that you can measure from your platform. And in terms of photon pair sources, one sort of major metric that you will see is what's called the coincidence to accidental ratio. And you can kind of think of this as the same as SNR, but with coincidence measurements, where you have some maximum number of coincidences compared to the background, which is usually normalized to 1. And I included these two plots here as a general indication of, if you want to maximize your brightness, maybe in the case of nonlinear sources, you can just pump it as hard as you want, right, until the thing burns or breaks. But as you can see here, you can only pump it so hard before you degrade the purity of the source or the fidelity of the source. In the case of coincidence to accidental ratio, there will be some pump power in which you achieve a maximum coincidence to accident ratio. And if you pump it even harder, the higher order emissions higher order emissions will actually corrupt the coincidence to accident ratio. So you don't necessarily just want to pump it as hard as possible.
Hey, Ian.
Yeah.
There is a question about what is the difference between the electric field strength and the brightness?
Oh, so I guess it would have to do with, classically you can think of, the power being directly proportional to E squared, right? But, in terms of these, quantum applications, what you're going to be detecting is not necessarily the electric field. It's like single photons, right? The exact what exactly the electric field is when you're talking about these quantum sources is a bit more complicated. And it's like you can think of fundamentally like how do you describe an electromagnetic field? Classically, the electric field is kind of like at the core of that. But quantum mechanically, typically you would think of it as the creation and annihilation of photons. And there is a formulation of what electric field is in this case, where it's kind of like electric field is actually an operator. It's not actually the state itself. Yeah, do you have a more?
Can I add something
just
a little bit to that?
Yes, please.
No problem. Yeah, when we're talking about brightness, we're talking about counting the number of photons. But each photon you can change the electric field of a photon very easily, actually by putting it in a larger or smaller volume, right? So that the energy contained in that photon could be distributed over a large space, or it could be confined to some nanophotonic device in which it has a very high electric field. So brightness refers to specifically this counting that we're doing of how many photons, not necessarily how large is the electric field of each photon.
Yes. So for whatever process that you're using, whether it's in terms of atomic systems or nonlinear sources, you can get significant benefits by putting it into an optical cavity or resonator cavity. And you can kind of intuitively think about it is that if it's not in a cavity and you're pumping it with some source of photons, the photon enters whatever active medium that you have and exits, and it only has that one time to interact with whatever medium you're using. But if you put it in a cavity, it has multiple chances to interact with that active medium, and like the total number of chances will be dependent on these external coupling parameters. One key metric that you look to characterize resonators is what's called the Q of the cavity, which is the ratio between the energy, photonic energy that is stored within the cavity to the energy dissipated per cycle. And when we talk about, the strength of the interaction, it's generally proportional to the Q of whatever relevant optical modes that you are using within the cavity. This is sometimes referred to as Purcell enhancement within a cavity, which has to do with the enhancement of the spontaneous decay rate, which you see sometimes in literature. So this to give you an idea of like what it looks like on a more experimental side of things, if you look at the bottom left here, where you have if you sweep the wavelength, you will see like periodic dips in transmissions that are regularly spaced from one another by what's called like this free spectral range of the cavity. So here's just an example here of like a nonlinear process where at a particular for a particular resonances where the resonances are aligned for the fundamental and second harmonic fields, you can get a really efficient nonlinear process here that has a very narrow line width. And in order to calculate Q, there's two general ways that you can do that for a cavity. One being what we do here, which is just a wavelength sweep, where the Q of the cavity is given by the ratio of the center wavelength to the line width of the resonance, or if the Q is actually too high and we can't resolve this with a wavelength sweep, we can also use what is called a ring down measurement, where we pump a particular resonance of the cavity and then switch off the pump, and we see how long it takes for all of the photons to exit the cavity. So the Q of your resonator is inversely proportional to the time it takes for the photons to exit the cavity.
Hey, Ian, you know what I'm thinking is Dan just told me before the class that taking more breaks was better. We have a 15-minute break scheduled like at 3 o'clock, but maybe we should take 5 minutes of that now.
Yeah.
We could take some time to stretch. And
yes. Also, I've been, kind of blazing through a lot of concepts. So if people have, even more questions or are just completely lost in some places, please let us know, and I'll try to clarify things as much as possible.
Okay, so 5-minute break where we at least pause content. We can either ask questions or whatever else. We've had a lot of great questions that I've been answering on the question and answer as well, Ian. If you wanted to take a look there and add.
Yeah, sure.
I may not have addressed everything. Okay, so here's an interesting one. Why is a thermal state bunching?
Oh, that is a good question.
We might need some like phone a friend, Mike Raymer, to help us out with this one. Because bosons in general like to bunch, but is there something special about a thermal state here that in fact, Brianna, can we promote Mike to be like a panelist so he can talk?
We can. Let me get to him here. See, Mike, you should have gotten a request to join as a panelist. Maybe. Oh, he declined to be promoted. Let's see.
Oh, he doesn't want to talk. Okay.
Yeah, I'm not sure if I have an intuitive explanation of why that is.
Yeah, so thermal states are among the most natural states that you get, right? Like just by shaking atoms, and they like and photons, being bosons, like to be in the same state, as opposed to fermions like electrons that don't like to be in the same state. And so they're going to bunch naturally when they emit. And so you actually have to do something quite special to make them not bunch. And so that's why lasers and single photon sources are, special and engineered to not bunch. But maybe there's something, a more intuitive way to think about the thermal excitation, like electrons doing their thing, that we explain bunching. If Mike has an interesting way to think about it, that'd be great. But otherwise, I'm going to have to think about it more.
We had another question in the chat. Is the state purity for a multipartite state measured similarly with a Henry-Brown twist interferometer? And I would just say, like, just speaking in a very loose way, you do use there's a way to measure fidelity as it's kind of like a summation of a bunch of different coincidence measurements that you can make. So there's like a very particular game you can play where you say perform a bunch of coincidence measurements while making single that also making a bunch of single qubit operations, or like you perform a bunch of local unitary operations, and then you make a bunch of coincidence measurements. And in general, you have like a wide set of coincidence measurements that you sum up in some way to measure the fidelity. Yeah, I'm just keeping it vague here because, you know, depending on what type of entanglement source, it's going to be a little bit different. But that is like in general the process. You can kind of think of like it as like you have this joint space, like this joint Hilbert space, and you want to measure projections on all sort of directions in that Hilbert space to characterize it. Like you're almost like taking a dot product, and based on those dot products, what kind of fidelity can you get? Yeah, that's kind of like the way that I think of it. But if you have maybe a more cohesive explanation, that'd be great.
Actually, I think we ought to move on.
Okay. Okay.
So we've got about 15 minutes left scheduled for the sources, and I think you might be about halfway through. So we might want to pick some highlights and then come back if we have time. Up to you.
Right.
Or I can compress some of the stuff we're doing later.
Right. Yeah, I'll try to sort of speed things up a bit. So just picking off where I left off. So there are like different platforms that you could use for constructing these single photon sources. One being like fiber, another being free space. And for this slide, we consider like nanophotonics. So like what exactly is the benefit of using nanophotonics? Well, you have the very obvious benefit is that you can confine these complex quantum systems into a very small space. So instead of if you need like several single photon sources, instead of it taking up an entire optics table, you have it all confined to be on a chip that is like a few millimeters by a few millimeters. But another benefit for using nanophotonics is the way that you could enhance the strength of whatever interaction you want is to take what the relevant photons, and we talked about like how you can change the electric field in two ways, one being you just introduce more power, or another being you take the same amount of power and you confine it to a smaller space. So that's like the general concept behind you can enhance the strength of whatever interaction you need to confining it into a smaller space. And in the case of parametric down conversion, that strength is inversely proportional to the square root of what's called like the mode volume. You can also get faster modulation. The one downside being that with nanophotonics is you tend to have fairly limited coupling efficiencies. Like if there are 3 schemes for coupling from, say, like a fiber-based system to a nanophotonic-based system here, which is shown here on the right. The most common what's being called like end-fire or butt coupling, where you simply just put the fiber right up to the waveguide, but you usually have at least 4 or 5 dB loss from that sort of coupling mechanisms. There are other more intricate methods such as gratings or evanescent coupling, but those also come with their own downsides. Yeah, I think I might skip this slide. This is sort of like if you want a preview of like what the theory looks like. If you have no idea what's going on here, don't stress about it too much. And I just give you a general concept of what's going on, where you have this nonlinear Hamiltonian, which produces some state. This is sort of like a Schrodinger type interpretation. Here's sort of like a Heisenberg type interpretation. And then ultimately, you can interpret this to get a rate of photon pairs that are emitted. And you'll notice for that waveguide, the sort of the bandwidth of the interaction is generally determined by like the phase matching and the pump profile, as well as any other external filters that you have on it. But for the resonator case, the rate of photon pairs is determined by the line width of the resonances that are using, as well as the brightness that you've achieved is also determined by the coupling parameters within the cavity. All right, so now that we have a source of single photons, how do we get to entanglement? Well, I should say that we have already seen one source of entanglement in the test for indistinguishability, where we have two single photon sources which are injected to a beam splitter. And if it's an ideal, if you have ideal single photon sources, you'll either get two photons in the upper path or two photons in the lower path. And so the total state that you get is in the quantum superposition of these two cases. And in general, this is what's called a noon state, which is generally useful for some applications like quantum metrology, where you have the variance in the phase measurement being inversely proportional to the number of photons you can generate in the noon state. And you can do something very similar for generating like a single photon noon state with just a single photon source here. The only downside of these noon states is that generating noon states for n greater than 2 tends to be very challenging. You need more intricate methods for doing that. And another downside in terms of quantum computation is that it's hard to construct what are called local unitaries for state manipulations. So usually you conceptualize these states in terms of qubits, where you say, oh, the case where you have photons is considered the one state, and the case that you have 0 photons is the 0 state. And the single qubit operations is that you want to be able to manipulate it so that you can flip it from the 0 to the 1 state, or vice versa. And you can imagine that it might be trivial to, if you have photons, to just get rid of them through loss. But the act of going from no photons to some photons is a very non-trivial task. Like, that's what we've been talking about so far. So yeah, in terms of local unitaries, like, that's not a straightforward thing to do. So another type of entanglement that you could use polarization entanglement, which you use what's called type 2 process, where you have your photon at 2 omega, and then you send it through a nonlinear crystal, and instead of generating like photons that are identical in polarization, you generate photon pairs that are opposite in polarization. And you could there are several ways to take these photon pairs and make entangled photon pairs. And here's just one example that I grabbed where what's going on is more readily apparent, where you have your pump here that is set into what's called a Sagnat interferometer. And when it goes around this interferometer, it can either go clockwise or counterclockwise. And you can see here, if you send it counterclockwise, you get horizontal polarized here, vertical here. And if you send it the other way, you get vertical here, horizontal here. So the total state, if you send in both polarizations simultaneously, is you get this Bell state of 1/square root of 2 HV plus VH. And the one nice thing about polarization, someone mentioned, like, why would you want to use polarization? One being it being robust in a sort of a free space platform. Another being that it's actually a lot easier to construct single qubit operations using half wave plates and quarter wave plates. The only downsides are that it's kind of really hard to manipulate polarization on an integrated optics platform, so using nanophotonics. And you also have to worry about if you're sending it through a fiber, which it's a vital tool for long haul communication. there's such a thing as polarization drift, where the polarization will drift in one direction or the other, and it's not fully deterministic and it's somewhat random. So you have to compensate for that polarization if you're using fiber communications. There are methods to do that, but it's not straightforward. Another sort of entanglement is sort of time-bend entanglement. I might kind of just speed through this, where you have like a photon pairs that are headed in opposite directions, and you have it either take a short path or a long path. And if you look at a particular peak in the coincidences at the other end, you can assemble this Bell state where it's a sum of both photons take the short path and both photons take the long path. You can also use frequency entanglement, which I kind of mentioned before, where if you tailor the phase matching and the pump profile in a specific way, you can get a state that is in an entangled state, rather than just like a correlated single photon pairs. The nice thing about this is that you can very easily achieve high dimensionality qubits using frequency, where instead of, say, just having 0, 1, you have 0, 1, 2, 3, 4, 5, so on and so forth, where you use a bunch of carrier frequencies and they're all in superposition of those frequencies instead of, say, just 2. And you can also use a resonator in this case, where the 2 photons in the photon pairs are allocated to separate resonances. Another really popular way to generate entanglement is by using something called dual rail entanglement, where a qubit in this form is represented by a photon either taking an upper path or a photon either taking a lower path. So in either case, you get a photon, it just differs where exactly it is. The really nice thing about that is that it's really easy to construct single qubit operations. Like, it's really easy to switch a photon from the upper path to a lower path using what's called a Mach-Zehnder interferometer. And you can do this on any platform, basically nanophotonics, in fibers, in free space, it doesn't matter. You can always construct that single qubit operation. And the way that it generally works is that you use like multiple photon pair sources and like what's called a post-selection process, where you only look at the quantum state if it has 1 photon per qubit. So you can think of it as like, in this simple case where you're constructing a Bell state, where 1 photon pair sources is responsible for producing the ones, the photons in the 1 state, and this source is responsible for creating photons in the 0 state. So if you post-select such that you only look at the state when it's 1 photon per qubit, you will actually see a Bell state pair. So cluster states are like a very a bit more complicated than like the source of entanglement that we've been looking at, where you just, with bipartite entanglement or Bell states, you have like 2 systems that are entangled with one another. But in general, you can have n greater than 2 subsystems that are all entangled with each other. And these types of states are commonly referred to as cluster states or graph states. And the way the reason that they're called graph states is that they can be represented graphically as a series of points where each point represents a qubit, and a line between those points where that line represents entanglement between those qubits. So in the case of graphically, this sort of representation is just a graphical way to represent 2 Bell state pairs, whereas this is, you can imagine, like a bit more intricate graph state. This particular state, where you have either all 0 or all ones, is known as like a GHZ state, and that's actually represented by this star graph here. And from these graph states, you can actually represent entangling operations through like on these graph states, where if you perform in in quantum communications what's referred to as a controlled Z operation that adds a line here, or something even more complex like a fusion operation where you merge the vertices and add a line. So how do we form these more complex cluster states? I might just speed through this, but there's actually a way to probabilistically entangle qubits just by using linear optics. So in this case, you have some sort of photon source of like single photons, and you have a collection of Bell states here, and we can use this what's called a probabilistic entangling gate to create the more complex state. It doesn't, create it with, unity probability, but the silver lining is that when it fails, we can tell when it fails. So I've been talking a lot about single photon sources, but that's not the only source that we would talk about. Another being, squeezed light. And essentially what that is when you measure the electric field using something called a homodyne receiver, which is shown here, there will always be some amount of noise in that measurement. You cannot precisely measure what exactly the amplitude and the phase of the electric field. And that is strictly due to the quantum nature of the light. Like, it doesn't matter how good your detector is, that uncertainty is defined by the light itself. So in terms of homodyne detection, you usually have like two different quadratures, like IQ, in phase and quadrature. In sort of like the quantum mechanics world, you would call this the conjugate position and momentum, but the Heisenberg uncertain relation means that the product of the uncertainties never falls below a certain value. So what squeezing is that you could kind of like pull a particular trick where you don't violate this Heisenberg uncertainty principle, but you can squeeze the uncertainty in one quadrature while increasing the uncertainty in the other. So if you have, say, just like what's shown here is actually just vacuum, even in measuring vacuum, you have some sort of uncertainty. But if you use this squeezed light source, you can kind of like take this sort of 2D Gaussian blob and squeeze it in one direction, where the amount of squeezing here, like the variance of those quadrature measurements are determined by the amount of squeezing R. And just to give you a more intuitive understanding of what's going on, of what's happening in this phase space versus what's happening with the electric field, you can kind of think of this sort of density in phase space corresponds. This is just what's called like a coherent state, which is the output of a laser, where you have that expected, sinusoidal oscillation, but there's some sort of blurriness in that electric field. It isn't exactly defined. And when you sort of like squash it, when you squeeze it, is that periodically within the electric field, that uncertainty like squeezes a certain amount while expanding in other parts of the electric field. So here's just an example of like coherent light, squeezed coherent light, and vacuum and squeezed vacuum. So once I might skim this a little bit, so apologies if I don't explain things all that well. So how exactly do we generate squeezed light? Well, one way we do that, if you look at what the quantum information theorists refer to as a squeezing operator for squeezing as quantum state, that is actually very similar to the Hamiltonian that we get from parametric down conversion. So it just happens that you could use spontaneous parametric down conversion to generate squeezed vacuum. I might skip over these diagrams, and since we're kind of short on time, but just to give you an example of like how exactly you generate this is that you usually take your laser, you double the frequency of the laser, and then you actually use that light that is double in frequency to generate your squeeze state. And then you interfere that squeeze state with the original laser to see those squeezing effects. So you can also get entanglement using these squeeze states. One way to do it is what's called two-mode squeezing. And it's the simplest case of using squeeze states to achieve entanglement. And the way that you make two-mode squeeze vacuum is just, instead of using a degenerate down conversion process, you use a non-degenerate down conversion process. So instead of emitting it in one mode, you emit it into two modes. And if you just look at the state in terms of Fock states or these number states, you can already see that they're entangled in photon number, but that's not necessarily helpful because you need to be able to resolve the number of photons, which is actually pretty difficult, which I will talk about later. What people usually, the type of entanglement that they usually look at when looking at these entangled squeeze states is that they're entangled in terms of their quadratures. So again, you have your X and P quadratures from homodyne detection. And if you look how the density in terms of like XA and XB, you'll notice this correlation here. So that is actually a source of entanglement. And I'll just briefly mention here that you can generate more sophisticated entangled state with squeeze states by using linear optics. I won't go into detail about that, but I'll just say that it's possible. Yeah, so that's everything about quantum sources. Do we want to stop here, or do we want to?
Yeah, so let's take a break and come back at 3:15 for continuous. That's a 10-minute break this time, or 9 minutes. And then we'll pick it up with quantum frequency conversion. And then our next segments we plan to be 15 minutes for each of the other quantum hardware. We spent quite a bit of time going over quantum sources because a lot of the concepts need to be introduced for the first time when you're talking about that piece of hardware, but you'll see some of them show up again on the other quantum hardware.
I'll be right back.
Okay. I'm going to do some more chat GPT.
I'll also just take this time to note that the course is being recorded, and the recording and resources will be shared. We're shooting for the first week of February to allow for some quality editing throughout. And then we will also have certificates of completion for all of our participants then as well.
Yeah, I'm going to ask our hard question to chat GPT. Why is a quantum thermal state bunched? See if it knows more than me. Yeah, that's a very good explanation. It's just not very intuitive. Maybe it's intuitive if you think about phase space and can conceptualize Wigner functions easily. Increased probability of finding the system in the ground state at low temperatures, right? The other thing, I wrote up some questions. Let me share a different screen. Okay, so while we're taking our break, here are some thought questions for you to consider that I thought were good questions to sort of test yourself to see if you're getting the overarching ideas that we're trying to convey in this introductory course. There are a lot of details that were included here, but these are questions you might think about just to see if you can get some of the core concepts. And ask for clarification or whatever you want to do. All right. Go back to the Q&A. Oh, Ali's asking, the temporal bunching of photons has to do with the Wigner function? Yeah, we didn't talk about the Wigner function, but it is a way to represent quantum states in what's called phase space, right? Where if you're familiar more with like electrical engineering or RF type stuff, you've got a phaser and it points to something in polar coordinates for the electric field, where you've got a phase and an amplitude, and it rotates around, representing a wave. Well, that phaser, or that point in phase space, can turn into a probability distribution of what is the electric field amplitude and phase probabilistically if you measure it, say, because you have a wave function with uncertainty. And the thermal state has a phase space distribution that turns out to be just a blob centered right around the origin, meaning the most likely thing is that there's zero electric field, but it has a random phase and a random amplitude with some probability distribution going out from there. And that is connected to this bunching behavior. Marco saying, anti-bunching seems to refer to having photons equally distanced rather than bunched together. What is the link to the explanation you have provided? Yeah. So anti-bunching means the photons are more likely to not be found together than apart. So it's probability distribution when you convert it into the time domain, right, means that you have photons coming, maybe say with equally spaced time. In the case of like a single photon source, you have one photon and another photon and another photon. They'll never actually be measured by a detector at the same time. They won't be overlapping. So that's kind of one way to think about the difference between anti-bunching and bunching. Okay, Bob Lance is asking about question 4. Radio communications more mature. Are quantum networks at our frequencies a good idea? Why or why not? Okay, so I won't answer this one right away, but I do think this is a great question to think about. If you have thoughts, you can put them in the question and answer, and then maybe I'll tell you the things that I've been thinking about on that line, along those lines. So I'm trying to interpret Marco's comment/question. By the way, ChatGPT gave a wrong answer, I think, to the anti-bunching question. In a classical non-quantum system, a light source that is emitting a stream of photons would produce a continuous stream of light with the photons being emitted at regular intervals. Yeah. Photons emitted at very regular intervals is not a feature of classical light. It's a feature of non-classical light. One of these effects is photon anti-bunching, which occurs when photons are emitted at irregular intervals rather than in a continuous stream. Yeah, it probably needs some refinement there. Ali says, can there not be a thermal state where all photons lie in a small time bin? I thought the only thing that characterizes the thermal state is the Boltzmann state, the Boltzmann states of a photon numbered measurement. No, so if you project a thermal state onto the photon number basis, you do get Boltzmann statistics. That is true. But the Boltzmann statistics by themselves, without something like the density matrix, Schrodinger's equation, don't tell you necessarily about the time of arrival. So you need something else, as Mike Raymer just alluded to, besides just one thing. Well, he was talking about the Wigner distribution, but yeah. And these are more advanced topics. Okay, while Ian gets back, let's discuss some of these questions. I think there was question 4. Radio communication is more mature than optical communication. Are quantum networks at our frequencies a good idea? Why or why not? So the primary reason why photons instead of other quantum objects are good for quantum communication is because they do not interact with environmental noise while they're traveling from source to destination. And one way to quantify that is to look, for example, at the ratio of the photon energy to the background noise energy. And so if you have, say, some thermal environment, background energies might be 1/2 kT, and photon energy is h bar times omega, right? So if you have RF photons, omega gets very, very, very small. And in fact, it's not as much, when that gets small relative to kT, you have noise problems again. So RF photons are very difficult for that reason. But there's no physics reason necessarily why they couldn't be used. Just practically, having low energy photons is not as good for single photon detection, for transmission without noise, for interacting with the environment. I was recently working on a project in which we were attempting to see whether we could do X-ray entanglement, right, at X-ray wavelengths. And that would be fantastic if you could make it work, because X-ray single photon detectors are almost perfect, right? You have such high energy in those X-rays, they hit the detector and you can get photon number resolution almost for free. And you know exactly when they're arriving. Whereas visible single photon detectors, we have to make them very, very cold. We'll talk about that in a minute, like using superconducting electronics to get something approaching like a near unit efficiency. Okay, Ian, are you back?
Yes, I'm here.
Okay, great. So let's continue on. I'll stop sharing my screen, and I think you've got the next 15-minute section, right?
Yes, I believe so.
Okay.
Here we go. Oh boy. All right. So pressing on here, another tool that we need that is commonly useful in a quantum network is what's called quantum frequency conversion. And the reason that it's useful is, like, a problem that we tend to run into is that the platforms that we use for storing quantum information are different than the ones that you would use to transfer and communicate that information. And when you're like addressing these systems with photons, the wavelength regions that are ideal for that are different depending on what you're doing. So for telecom communications, just for minimal absorption for telecommunications, you'll want to communicate between 1.5 and 1.6 microns. But for, say, storing or addressing quantum memories, you need light that is between, for example, for diamond vacancy centers, between the 600 and 800 nanometer range. You generally need a whole range of visible light for quantum dots, and for superconducting qubits. That's actually, you would use RF for addressing superconducting qubits. So that's like in the megahertz and gigahertz range. Yeah, so this is sort of like illustrating the general idea for conversion, where you have photons coming out at a certain color, you change it to another color to go through the fiber channel, then you change it back to whatever color you need to address it to the quantum memory. And this is sort of illustrating that depending on what shift you need, you would actually use different methodologies depending on the order of magnitude of the shift, as well as the wavelength regions you use for that shift. And I should also mention that this sort of quantum frequency conversion has also been proposed to compensate for any distinguishability in your quantum network. So yeah, if you have two single photon emitters that are different in wavelength, you could use quantum frequency, you could theoretically use quantum frequency conversion to sort of shift it back to make the wavelengths identical. So no matter what type of frequency conversion that you need, you generally need some type of nonlinear interaction to facilitate that frequency conversion. And this could be optomechanics, electro-optics, optomagnetics. You can also use atomic interactions. And you can see here that these sort of nonlinear interactions are depicted in terms of combining and dividing photons here, where you have your first order process just modulating the single particle in some way. Second order process, you combine or divide photon, or I should say quasi particles, not just photons. In a third order process, you can combine two particles in it, excite two particles. You can also technically have this type of interaction where you combine three to get one, or put in one and get three, but those interactions tend to be really weak. So it's exceedingly rare that you would actually use those type of interactions. And I should also mention that you can combine nonlinearities to form one effective nonlinearity. So here's just an example of combining a first and second order process to get one big second order process, or combining two second order processes to get a third order nonlinear process. And in general, no matter what type of nonlinear action you're using, you typically not need some pump to facilitate that type of interaction, where the strength of that interaction scales as the square root of the number of pump photons. So for whatever, when we do conversion, frequency conversion, we usually use like some sort of resonator structure. And the way that you formulate that theoretically is we use what is called Heisenberg equations, where we see how these creation and annihilation operators evolve with time, and what's called the input and output relation of a cavity to determine the efficiency of that interaction. So, you know, doing a bunch of math and figuring that out, the conversion efficiencies are often given in terms of what are called cooperativities and extraction ratios, where the extraction ratios are just the ratio of the external coupling to the total coupling parameters. And the cooperativity is also given in terms of this coupling, but also has to do with the strength of the nonlinear interaction. And in terms of like combining nonlinearities, this is sort of what I was talking about, where you can have sort of a direct conversion scheme where you have some particle that has some resonance that directly couples to another resonance at a different wavelength that you use for frequency conversion. Or you can have some sort of intermediate stage where instead of going directly from one frequency to another, you go from one frequency at one medium to another frequency at another medium, which is then changed to another frequency at another medium. And I'll go over some specific examples. You also have to consider what your noise and bandwidth is, what kind of noise you sort of add to the system when you do this type of conversion. And there's usually two possible ways to introduce noise into the system. One being thermal noise from just black body radiation from your system. So just like if your parts are at a certain temperature, that introduces noise. But in some other cases, you have to worry about spurious nonlinear interactions. And basically, this is just any sort of nonlinear interaction within your system that you haven't designed for. It happens like quasi randomly. So there's two different types of conversion that I'm going to be talking about. One is sort of like ones that's strictly in the optical range of things. But the more interesting one to talk about is to say the microwave to optical. So I was talking about superconducting qubits, which is like a really appealing platform, but in order to communicate over long distances, you need it in the optical wavelength. So, but for microwave to optical frequency conversion, thermal noise, like noise from black body radiation tends to be the dominant source of noise. And you can see here in terms of both direct conversion and single stage conversion, what that added noise looks like. You also have to worry about the bandwidth of the interaction, which is generally dictated by the coupling efficiency within those resonators. And it's nice to see that, like, whether you're talking about efficiency, noise, or bandwidth, you generally want a system that is like highly overcoupled, where the nonlinear interaction within that cavity is a really strong one. So I'm going to briefly talk about optical quantum frequency conversion. Not that it's not interesting, it's just very similar to kind of like what we've talked about already, where you use optical nonlinearity. You can kind of think of it like you're using like second order nonlinear interactions, but in a slightly different scheme. Instead of using spontaneous parametric down conversion, you facilitate down conversion or up conversion or second harmonic generation, which is facilitated by another external pump laser. One thing about optical QFC is that you tend to have to worry more about any sort of spurious nonlinear processes for this. For example, any sort of fluorescence that might happen, or Raman scattering within your waveguiding structure. And with the current sort of technologies that have been available, we've seen efficiencies up to like 20, I think I've seen like maybe like 30 and a little bit above percent conversion efficiency using these sort of nonlinear crystals. And I believe, I don't know the exact details. I believe Don Tousley goes a little bit more in detail into why this is, but in order to have reliable quantum frequency conversion in a quantum network, there's actually like a 50% efficiency threshold that you meet in order to reliably transmit those quantum states.
Yeah, it's a percolation theory argument, but yeah, if you want to know more about that, you should take Don's course.
Right. So I'm going to go over like a few methods that for microwave to optical frequency conversions. One way to do it, which is by far the most popular way, I believe, is called optomechanical frequency conversions. And it's essentially using phonons or sound to facilitate that. And the nice things about photons is that they are at microwave level frequencies and optical level wavelengths. And using that method, you can actually obtain really high cooperativities with optical mechanical frequency conversion. The way it generally works, you can kind of see in this picture right here, if you maybe squint enough, is that you generally have like a membrane that hosts the acoustic vibrations, and you excite the membrane from using your RF signal and piezoelectrics. And this membrane actually modulates the like a optical Fabry-Perot cavity that it's in. So that's how like the general methodology of how you convert an RF photon to an optical photon. And there are, of course, different schemes that people have used in order to make these optomechanical converters. One being like you could use bulk optics, which is here, which you can get really, really high Q out of, or you can use a more integrated platform where you can have a very large mode overlap and a really small mode volume. I believe the only downside to using this kind of modulation, or not modulation, this type of frequency conversion scheme is that the acoustic transduction efficiency for like the piezoelectrics, the efficiency of converting a photon into a phonon is actually fairly low. But I believe it's actually gotten as close, it's gotten the closest to actually achieving that 50% threshold. I believe there is one study that got up to like around 47%. So this is generally what is seen as like the most promising platform for converting RF photons to optical photons. So another scheme that people have investigated is what's called electro-optic frequency conversion, where it's actually a direct conversion scheme, where you have the electric field from the RF field is used to modulate the optical refractive index of a material within a cavity, where you need to use second order nonlinear material like lithium niobate to facilitate this interaction. You know, this is generally a much easier or like a lot simpler to fabricate than like optomechanical frequency conversions, but the efficiency so far that people have been able to achieve is generally just not as high. A third one, which I thought was really interesting, is what's called magnon mediated conversion, where you actually use magnetic fields to facilitate that. The appeal of using these magnetic devices is that you can get a very large range of tunability and a really broad bandwidth with these magnetic devices, where I believe it's yttrium iron garnet. Please excuse me if I mispronounce that. I'm not a chemist. That is a very popular material for these types of magnetic devices. So you can get these very strong coupling between what are magnetic quasi-particle magnons and microwave photons via a linear magnetic dipole interactions. And then the way that you convert that into an optical photon is through what's called the Faraday effect, where the polarization of a photon actually rotates in direct proportion to the magnetic field that it experiences. Yeah, that was, and yeah, that is like my general short overview of what quantum frequency conversion is. Do you want to take over?
Yeah, let's see if you can stop sharing your screen. I'll start sharing mine. Okay, so we've talked about generating quantum states using single photon sources or nonlinear sources. Now you have your quantum state, maybe it's not the right frequency, so then we talked about converting that quantum state to an optical frequency or an infrared frequency that we can transmit over large distances. Now we're going to talk about that transmission problem. How do you get photons from point A to point B efficiently without losing them, without making them indistinguishable, without adding noise to them, etc.? you have essentially two options, free space or fiber. Let's see, I can go to present mode. That would make it easier. And when we think of free space, we often think of lenses, mirrors. You've got to keep that, instead of being in a waveguide, right, it's going to diffract. But it's really our only option if we say want to go up to satellite. I think it's just fantastically phenomenal, maybe even magical, right? Some of the very first quantum measurements, or the HBT, Hanbury-Brown twists, right? They were measuring the angular diameter of Sirius, the brightest star in the sky. And to think that the quantum state, right, of photons produced, hundreds of light years away, thousands of light years, could make it all the way to our atmosphere. And then right there at the very end, that's when the quantum state has the most noise imparted to it, is amazing to me. So we know we can transmit quantum states very, very far distances, even in free space. It's a lot more convenient for Earth-based systems to use optical fiber. Imagine a free space fiber network. We do it with RF, I suppose, but importantly, when you think about transmission, one of the key things to know is that you cannot have amplifiers in your channel. The no cloning theorem from quantum mechanics prevents us from copying a known quantum state with perfect fidelity. And amplification, like I mentioned before, is like copying, so you can't do it. When you're considering the logistics of putting your fiber links or your free space links, how far should you go from one link to another, between one node and another node? You have some tension or a trade-off in place. Economics and logistics require that you would like to have a fewer number of quantum repeaters and memories. When you have to convert the light back into its atomic or matter-based entanglement. But loss is exponential with distance, a Beer's law type absorption. So that sort of suggests that you might want a higher number of repeaters. So depending on the topology that you're trying to design for your quantum network, you have to balance economics and logistics with loss. If you're building a free space quantum network, you've got to think about all the ways that you could add noise or loss to your channel, like reflections. You've got detector surfaces even at the very end, getting on and off chip. For example, you have misalignment of your optical elements, you've got atmospheric turbulence, just dispersion, particle scattering, all these things in free space that can affect the quantum state that you're trying to transfer from one place to another. In fiber, you've got free single mode fiber, multi-mode fiber, and if you say you put your quantum state into a single mode, and then somehow some scattering in the fiber scatters it into one of the other modes because you use the wrong type of fiber using multimode fiber, that's a problem. Now you don't have states that are the same as the one you put in. You've got wavelength dependent loss. And as Ian was saying, right, when we're talking about what wavelength we'd like to send through a fiber, we're going to immediately think about 1550 nanometers because that's where our lowest transmission loss is. You get about 25 kilometers for a 1/e attenuation length. So that's something, tells you something about the natural length scale that you might consider. Kilometer type scales, 10 kilometers maybe between elemental links. And just getting light to and from a fiber is a significant challenge, perhaps one of the greatest challenge right now in terms of loss that's limiting quantum network scalability. Just getting light from your quantum emitter and receiver into fiber. So I thought I'd just spend a minute and look at one current area of research that's happening to try to solve this problem. I happen to be involved in this one. So if you look at just a diamond quantum emitter that's going to emit, say, a single photon from this artificial atom within some diamond qubit, you're going to release that photon, and the goal would be to couple it to this fiber here. Well, if you're, if you have something like an atom, it's going to want to emit in like a dipole in almost, 4 pi star radians. And so how can you capture all that light and put into a fiber, especially when, your leak efficiency, the maximum rate is completely dominated by the efficiency at which you can do that. For diamond, you've got 2 problems. One is it doesn't like to emit into the right frequency, or what's called the zero photon line. And then, of course, you have your collection efficiency problem. So how can you fix that? One approach that different researchers, including myself, are looking at is using something like a topology optimization to etch a pattern into the diamond to cause it to emit up and have a very high far field collection efficiency. And here's some initial patterns we found that seem to do much better than what you might naively expect. My student calls this one here the Eye of Sauron. It does a pretty good job. Anyway, you have an efficiency. It can be broken into 2 parts. One is just getting the matter qubit state into the photon itself, and then getting the photon into the fiber. So you have to optimize for both those things. It's a hard problem. And it's one that is currently limiting a lot of the scalability for at least the Center for Quantum Networks, the diamond-based qubit and matter interactions that we're trying to optimize. Okay, so here I had planned a pause for maybe discussion or questions. If we're considering our quantum telescope, and we've talked about sources and frequency conversion and now transmission, what type of losses might we need to consider if we were to build such a telescope, and what trade-offs would there be, say, from using fiber to connect our telescopes for entanglement versus free space, etc. So you can think about that for a minute, and then we'll go on. Okay, so obviously the sources of losses we need to consider, right, are just setting up this entanglement channel, right? The longer your baseline is, the more lossy it's going to be to try to distribute that entanglement from one place to another. So that might limit you. You've got also losses within the telescopes themselves. If you've got, right, this entanglement and this quantum memory trying to hold on to the state, it's going to interact with this environment and it's going to get noisy. Would you want to consider free space or fiber here? Well, that's a great question. Fiber you might enjoy because you can connect it up more easily, and there are ways to do synchronization and timing and maybe keep your photons in the right mode, but then maybe you have dispersion, maybe you have thermal gradients that are going to affect your entanglement, but it can be done. If you go really far distance, if you wanted to make, a quantum telescope like using maybe other satellites, then of course you have to do free space. And there's a lot of other things to be considered. And I don't think it's obvious necessarily which one you should use. Okay. Okay, let's move on to quantum memories. This will be a very brief introduction just to introduce you to the types of things you might think about when considering how to store your quantum state in matter or in some atomic system while you're waiting for some other operation to happen. So you've got your entanglement links, and oftentimes you want to wait to do some kind of analysis or even just setting up the entanglement. You have to wait for photons to arrive from different places, and so you want to store the quantum state in some place and waiting for that. That's why we need quantum memories. So in the very first, or the overview part of this lecture, I talked about one type of entanglement distribution in which we had a photon state that was in an HH plus VV Bell state is what we called it. And we distributed it so the one photon, say, went to one party, another photon went to the other party. And they were able to capture those photons in atoms so that they could then maybe measure or manipulate them or have magic dice in that case. So let's take this nonlinear emitter and suppose one use case for a quantum memory is the following. Let's say it's emitting 2 photons which are entangled, and instead of sending both photons to a remote party, Alice might want to keep one around so that she can entangle her qubit that she has locally with a qubit that Bob has. So she takes one of these photons and she stores it in its matter state, a memory qubit, while the other photon goes over to Bob, and he eventually will capture it and turn it from a photon quantum state into a matter or atomic quantum state. Now, once Bob has that photon captured, he can either make a direct measurement of the photon and immediately use that entanglement to do something important, maybe generate a key or route some other signal. Or if he has a quantum memory of his own, he can also transfer that quantum state to his quantum memory and then hold on to it. And now we have entanglement that can be stored and used for some later purpose. Maybe it's some joint measurement they want to do together, or a computation, or it can be a resource, entanglement as a service that the network is providing for the users of the network. Okay. Ian, if you could help me out with the questions, let me know if you see any there that we need to address.
Yeah, no problem. I think one of them was kind of answered along the way, but it might be helpful to go over it. It's one was like, why does a repeater not violate the no cloning theorem?
Okay. So let's see. Why does a repeater not violate the no cloning system? The simple answer is that you have to actually destroy the quantum state that you started with. So you're not actually cloning it. You're like destroying one and creating another. So that if you're willing to do that, then you can get around the no cloning theorem. So inside the cloning means you have an additional copy, which is why amplification is not allowed, but repeating is.
Another question is, I guess this is sort of more of a sort of platform-based question. It's like, why would the photons only be absorbed if they are in the H state? And generally what I think is like, there are only certain transitions allowed within like an atom, like any sort of atomic structure, like whether going to one orbital to another. The photon that facilitates that, there are certain what are called selection rules for that determines if that transition is even possible in the first place. And one of those requirements might have to do with the polarization of the incoming photon.
Yeah, right. You could engineer your atomic system to be only sensitive to, light oscillating, say, in one direction versus the other. It was an arbitrary choice I made when making this cartoon, but it's certainly something where you can have polarization dependent absorption. In fact, this is a key part of the diamond-based quantum systems that we're building for Center for Quantum Networks, is that you get a polarization dependent reflection, actually, like spin-based reflection. So that's something that Dirk England will go over in his course, I believe, at the end of the week.
Question about again, this has to do with the no cloning theorem, I believe, as like, is there a fundamental reason that a quantum repeater or memory cannot increase the power of the output photon?
Well, technically speaking, you might be able to increase the power if you're able to, say, compress the photon. Maybe it's right, a photon has a certain amount of energy and it has a wave function that extends over some time period. And so maybe you're able to apply some dispersion and compress it so that that same photon traverses this, over a shorter time. So maybe that's power, but average power, no. Again, you can't take a repeater and add it. Energy conservation must apply. Okay. Here's an example operation that turns out to be the most basic fundamental operation for building a quantum network, for most quantum networks. And I believe in Michael Raymer's course, he probably went over quantum teleportation, but just to remind you what's going on here, if you didn't have that course, let's say you had some shared entanglement already between Bob and Alice. So you prepared that using one of the techniques we've talked about. And then you wanted to use your quantum network, in this case, to transmit data or some quantum state that Alice has in some other part of her system. You'd like to send that to Bob. So quantum teleportation says you can do that if you do the following operation. If Alice would say, take this, her qubit that happens to have entanglement with Bob, and entangle that one also with this qubit to be teleported. So now there's two squiggly lines representing entanglement here. Both of them end on this qubit that Alice has. And then what Alice does is she makes a measurement on these two qubits, right? One of which is entangled to both the qubit to be teleported and to Bob's qubit. When she does that, she's going to get two numbers, two classical numbers, either zeros or ones. And if she sends both of those numbers over to Bob, Bob can do some operations locally on his own qubit, because that's enough information, it turns out, to reconstruct the exact qubit that Alice has. And you can do that with unit fidelity. So as long as you're willing to destroy Alice's qubit, that it no longer exists, by measuring it, you can do the teleportation and transfer it over to Bob. And that answers a little bit of the question about no cloning and how it's different. And you can use that, right, to transmit quantum states or move them to different places across the network if you're clever about how you do teleportation-like operations. So you can extend, say, this link level entanglement, right, so that you have something that extends to other network nodes if you're able to do, if you want to do similar type operations between Alice and Bob and, say, Bob and Charlie. And now you can perform operations on these two qubits that are in the middle, operations known as purification or entanglement swapping or other logic that need to take and make measurements locally here between entangled particles. So when you're thinking about what makes a good memory, you think about, okay, well, it has to hold on to the atomic state, to the quantum state for long enough to set up all this entanglement. It also has to be able to get the photons in and out very efficiently at the wavelengths required with, say, the temporal profile of the quantum state that you'd like to send in and out. They have to be indistinguishable. So it has to be able to do all these things while having a very controlled interaction with the environment. You only want it to go in and out when you tell it to do that, and not when, say, some noise or some extra things happening that will destroy your memory. You build this up by having many, many potential qubits or many, many atoms in registers. And because generating entanglement between two parties can be probabilistic and not very good, oftentimes what you do is you take your register and you try many, many times across different qubits. And the job of this guy in the middle is Don Towles is going to talk a lot more about these layers of protocols, these management layers that control what's happening. When it sees a success, say, between two qubits locally, it can use those and say, okay, I've got a couple. In fact, if it sees success on multiple, it can use multiple successes to purify and make one successful entanglement operation stronger. Okay, so then you can do teleportation-like operations, and you can generate long-distance entanglement in which all these qubits in the middle are no longer participating, and you've transferred that entanglement over longer and longer distances, thereby building up your network. So memories are really important to be able to do this. Okay, there's a picture of what I just said. Okay, so we need memories for timing, for synchronization, and obviously they're very critical for quantum repeaters as well. And in Dirk's class, he's going to talk in more detail about the types of quantum repeaters that we're building for the Center for Quantum Networks and go into a lot more detail there. Today is just meant as an introduction to why you'd want one. Okay, as we asked ChatGPT, and it answered us, there are many different types of quantum memories. The AI knew about some of them. You're looking for a memory, any state that can be very long-lived and can be converted to and from photons is a great candidate for quantum memory. So we've talked about ground and excited state of atoms. You can use the spin of an electron. You can use the spin of a nucleus. Those tend to be very long-lived. And many diamond color centers have the advantage that you can transfer using only microwave control quantum states from electron spin to nuclear spin. You can use even the relative positions of atoms. Defect centers, quantum dots, all these type of atoms are ones that have properties like this that you can use. And then, of course, there's superconducting Josephson junctions. There is a line that's very fuzzy between making a quantum memory and being able to do operations on that quantum memory and actually building up a full quantum computer. Once you start doing a lot of these operations that I'm talking about, weighting, synchronizing, being able to manipulate quantum states so they can be ready to transmit in certain modalities and ways and protocols, you've essentially made a mini quantum computer at your network node. And so the line between quantum communication or quantum networking and quantum computing is blurry and fuzzy, and they need to really coexist and be developed at the same time. Okay, finally, I wanted to reemphasize something that Ian said about the importance of cavity enhancement. It's really difficult to get photons in and out of quantum memories, not just because of the collection efficiency problem, but because photons do not like to interact with atoms that much naturally. And so using cavities or nanophotonic devices allows you to have multiple passes or increase the interaction strength between your photon and your potential quantum memory. And that turns out to be really important. Okay. I think I'm gonna skip this part for right now. For time, we're at 4 o'clock. We have 30 minutes left. So Ian, I think we've got detectors left, and then we'll finish up with some concluding thoughts.
Yeah, all right. Sounds
I'm gonna
good.
stop sharing.
Okay. Let's get down here. Okay, here we go. You guys can still hear me, right?
Yeah.
Okay, cool. Uh-oh, what's going on? Sorry about that. All right, so quantum detectors. So as we've gone over several times, like usually when you're dealing with quantum singles, you're dealing with single amount of photons. So the relevant quantum state that you're measuring is typically on the single photon level. And depending on the type of application that you're doing, you might need many single photon detectors. Here's just an example of like one quantum application called boson sampling, where you're sending like a bunch of single photon sources through this unitary operation, and then output, and you'll need like something like 60 single photon detectors to gather the relevant coincidence measurements. And just to reiterate, like the detectors end of things can be, just as important as the, sources or the memory side of things, where in terms of like a quantum network, the secret key rate of that quantum network is directly proportional to the efficiency of the detectors that you use, as well as the error rate within your quantum network has to directly do with something called a dark count rate within a quantum detector. So the relevant metrics that we're generally going to go over is detection efficiency, as in if a photon hits your detector, how likely is your detector going to register a click or recognize that that photon was there. There's a dark count rate where even if no photons hit your detector will still have like clicks that indicate falsely that there's a photon there. There's also something called dead time, where if the photon hits the detector, it actually cannot detect another photon for a certain period of time. Like the mechanisms within the detector, they need time to reset before it's capable of seeing another photon. And another one is called timing jitter, where we've talked about the timing at which photons hit the detector is really important for measuring whatever relevant statistics. So there's some uncertainty in that timing measurement that's called timing jitter. So one of the oldest single photon detectors out there is called oh my God, what is it? A single photon avalanche diode. There it is. So this diode is basically just like smashing together of two different doped materials, where it's this diode is operating in what's called Geiger mode, or a reverse bias voltage that is greater than the breakdown voltage. So when a photon comes in here and creates an electron hole pair, it causes an avalanche of current to come out of the photodiode until it's reset. So the efficiencies of these types of detectors can get up to 85%, 85% if you say use it in combination of a cavity. The dark count rate can be reduced by reducing the temperature of it. The one downside of these types of detectors is that there is a considerable amount of dead time, since like that is the detection is dependent on these electron hole generation. These electron hole pairs can actually be trapped in trap sites, and so before you can actually detect another photons, these trap sites need to be depopulated. And this can, depending on the type of detector, this can take tens of nanoseconds or even on the order of microseconds. And the timing jitter and efficiency, there is also a trade-off between timing jitter and efficiency, where you can see like the more volume in which electron hole pairs can be created, that's going to add some uncertainty into like at what time did the photon hit the detector. But obviously, the more volume it has, the more likely you have of this electron hole generation. So there's that trade-off there. And there has been some research gone into these SPADs. They tend to be a little bit more efficient at higher frequencies. So if you have a photon at lower frequencies, people have investigated and have shown that you can increase the efficiency of the detection process if you first upconvert the photon from one frequency to another and detect that upconverted photon. Another type of detector, which is far less common, I actually don't really see this type of detector all that much. It's called a QDOGFET, or quantum dot field effect transistor based detector. So you can basically think of it just as a regular MOSFET, like a field effect transistor, where if you have a incoming photon that is absorbed by this, photon active material that emits an electron hole pair, that hole pair gets absorbed by like these series of quantum dots here, which basically modifies the conductivity of the channel. So all these have been investigated, these operate at like very, very low detection efficiency, around 2 to 12%. But the one upside is like that the amount of dark counts that you get out of these types of detectors is actually also really low as well. Yeah. So by far the most exciting types of single photon detectors that have been investigated the most over the years are detectors that use superconducting technology. So there's like a bunch of varieties of the different types of superconducting detectors, such as transition edge detectors, tunnel junction detectors. It's also something called a microwave kinetic inductance detector. But no matter what type of detector you use, most of them tend to rely on what the material transitioning from a superconducting state to a normal conducting state, because that transition edge that change in transition tends to be really sharp. But by far the most popular of these superconducting detectors is what's called a superconducting nanowire single photon detectors, where you have these series of wires that are, say, like only like hundreds of nanometers across, that are operated just on the edge of being superconducting. So when you have a photon that is incident on this superconducting wire, it actually excites it out of the superconducting state, or some people call it like a Cooper pair breaking, where it goes into a normal conducting state where it has some amount of resistance. And of course, with amount of resistance, with a current constantly flowing through your superconductor, that's going to register as a voltage spike in time. So you'll see here with a absorption of a photon that you see that spike here, and that spike in voltage where it goes from normal conductance, and then as time goes on, it gradually settles back down to the superconducting state. Of course, with superconductors, that usually requires some sort of cooling apparatus that are around 4 Kelvin or less. But since we are dealing with nanowires, which are very small, the one really a good upside of this is that they tend to be like very fast detectors. Like there's very little dead time, and the timing jitter is less on the order of like tens of picoseconds, which is really good. And with the use of cavities, you can get a efficiency for these detectors upwards of 90%. So I've been mentioning that, like, when photons are incident on these detectors, they're registered as clicks, right? So you see a click which has some sort of timestamp which indicates that a photon is there. However, the one downside is that most of these types of single photon detectors, they cannot by default detect if multiple photons are incident on the same detector, like at the same time. So if instead of a single photon, you have 2, 3, 4, by default, you can't really tell. All you can tell is that there's one or more photons that have arrived simultaneously. However, there have been some people who have been looking into adding this, what is called photon number resolving capability to detectors. One method of doing this is just by very carefully studying the response curve of whatever detector you have. So in terms of like, you can construct this histogram of like the different voltage curves that you can get as a function of 0, 1, 2, 3, 4 photons, and you can try to use that to distinguish, instead of a single photon, there was actually 2 photons that arrive. But of course, this is, of course, you can only do this so much between like detecting 1, 2. You maybe can go up to like 4 or 5, but I haven't seen really anything beyond that. Another method that you could use is called like a pseudo photon number resolving detector, where instead of just using one detector, you actually use a bunch of detectors, and you use space and time multiplexing to sort of try to attempt to separate out multiple photons at a time. So you have this beam splitter here, and if 2 photons arrive simultaneously, ideally you would have them separated into two of these paths here, and then two of these photon detectors would measure separately a single photon, and that's how you know, oh, there was two photons that arrived simultaneously. And this is a lot simpler than trying to do it the other way, but the only downside is that it separates these simultaneous photons only with some amount of probability, like that the process of separating those identical photons is not guaranteed. But for a lot of applications, you know, in terms of measuring like the fidelity of states, you can still get some level of improvement by using this pseudo PNR detector rather than just the regular single photon detector. And here's just a overview of some tables I found with all the different types of detectors. You can see here with SPADs, you can get up to like 70, like 80% detection efficiency. And you can see with the superconducting, where you can operate SPADs at around room temperature, or maybe a little slightly cooler. For the superconducting, you have to go to like the single Kelvin level. And in terms of like superconducting nanowire photon detectors, I just want to reiterate that is by far like the most exciting or the most looked into type of single photon detector that people have been using. If you use niobium nitride here, you can get like really high detection efficiency up to 98% while having really low time jitter. And yeah, I think that's it on my end. I think you're muted.
All right. Thanks, Ian. I'm just going to switch display settings, see if that works. That didn't work. That's okay. All right, so let me go to the last thing I wanted to do today is just remind ourselves what we've covered and leave you with, again, the quantum telescope application, which I personally find one of the most far-reaching, exciting, I guess you could think of it, pie-in-the-sky goals that maybe in 20 or 50 years, if we were able to accomplish this, I think it would be quite revolutionary. There are a number of applications like that. They all involve the correlations of quantum superposition states. That's the thing we call entanglement. So most of this course today has focused on the hardware necessary to create and distribute entanglement and the things that might go wrong, and just give you an overview for some of the practical types of things you might want to consider. So as a reminder, our quantum telescope had as its input state this quantum superposition given to us by the starlight of a photon either arriving at the right detector or the left detector. We know that there's a difference between those two paths in terms of a phase, and so you could, and this is the way telescope arrays are built today, you could have a solution in which all you do is just measure the relative phase, and this is in fact what phase arrays telescopes do. And they have to control the phase or mathematically reconstruct it, but getting the phase correlation, the correlated phase between these telescopes is the problem, and that's what we want to fix. And so we introduced entanglement and correlations as ways to perhaps have that phase correlated. And now that you've seen a few of these pictures already, you can identify our entanglement, and you could think about how you might want to generate some type of entanglement between these two nodes using sources which produce entangled photons and send them across some channel, whether it's free space or it's fiber. And then once there, you need to store that shared entanglement or those correlated superposition states in some kind of memory while waiting for these photons to come. And you'll have to have a lot of memory, right? Think about the number of photons you'd like to collect from the starlight. Each one of those is going to require its own individual qubit stored in memory, unless you're going to do some other type of continuous variable state, perhaps. You also have to have a way to have these two interact inside, right? So they have to be able to store it and then on demand or at some later time produce an interference or some kind of joint measurement between your entangled state and the stored state of the photon to matter that's coming into your detector. These are all really hard problems, especially when you consider, right, that the Earth is rotating and you have to track things to within, sub-milliradian tolerances. You've got noise going on, thermal noise, electronic noise, all kinds of things. And so papers are starting to come out that analyze scenarios like this that are applicable to other quantum entanglement application spaces. And they're all really hard, but they're all really exciting. So I guess I'd like to convey at the end of this course also my personal excitement for, if we can get this right, some of the things that we can do in the future for our children and grandchildren. The types of technology that they'll have could be quite amazing. Okay, so in summary, in review, quantum networks, their basic functionality is to distribute entanglement. That entanglement can be used for a number of applications, and we've considered today some of the hardware or the key hardware components that are needed to distribute entanglement, including sources, transmission, memories, detectors, and frequency conversion. What we did not cover was the immense importance of the classical hardware needed on top as another layer to control everything that's going on and to interpret and make decisions on the measurement outcomes that we make on all of these entangled pairs and what to do with it, how to schedule it, how to route, all these things. Don will cover a little bit of that, but Dan Kilper in his lecture, hopefully it gets recorded, also covered a lot of the classical networking needed for the quantum network. We talked a little bit about the quantum application, the application of a quantum telescope, and I hope you find that as exciting as I do. And with that, we will end the course and say thank you to all for participating, and hopefully you've learned a little bit. I'll hang around for just a bit if people have some follow-up questions. Otherwise, we're done for today.
Thank you so much, Ryan and Ian. I'm going to put in the chat a link to our post-survey questions. When you close out of the Zoom, you should also be directed there. We'll also be following up with some emails with the recordings and the slides as well.
Okay. And for those still around, I wanted to thank you to Brianna Moreno, who's been organizing all of this for us and is our administrator in the background, and especially to Ian, who spent hours and hours with me working on some of the slides and lecture content. This is his first time giving a course like this, and I thought he did pretty well. So thanks to Ian for that.
Thank you. Yeah, I thought it was generally it was very illuminating trying to find a cohesive way to explain all of these complex topics, even though I might have not been super successful about that. And if I confused some of you, I'm really sorry about that. But yeah, it's generally a pretty great experience. Got a lot of refresher on a lot of topics that I really should know anyway. So yeah, it was a great time.